who is having interest in the field of quantum computing. He has completed his bachelor degree in computer science from the University of Delhi with the CGPA of 9.86. He is pursuing his master's from University of Delhi. Besides, besides that, he is having a startup that solves the computational problem using quantum computing principles. He leads the quantum computing division, and some of his achievement in quantum computing are: he is working on animation quantum algorithm. He is a mentor for Indian Quantum Machine Learning Challenge. He is a mentor for IBM for Quantum Challenge 2020, and many more. His achievements are further. He has worked the projects like Quantum Genetic Algorithm, and he has another project is Hearing Quantum Evaluation. I welcome you, Abhigyan sir. Over to you.
Yeah, thank you, ma'am, for such a vivid, descriptive introduction. So yeah, my name is Abhigyan Mishra. I am a master student in the university, and I'm also senior quantum computing developer at you can say a startup, but it's like connected, associated with IBM. So without wasting any time, let's get into the discussion. So before I start the actual you can say the workshop or the session, so I did go through the you can say the schedule, and I sort of have an idea like what kind of information, what kind of knowledge you all the attendees have right now. So the thing is, I understand that I mean, giving everyone a benefit of doubt, I'll assume for this whole session that everyone here you can say just has about you can say quantum computing 101 knowledge. I mean, I'm not expecting everyone to be at a level at that I can expect them to understand every aspect of mathematics. So even if at certain point you feel like certain things are they seem difficult, or you can't seem to grasp them, don't worry. It's a 2-week school, and after I went through the schedule. So there are certain topics which you'll be covering in the latter you can see in the second week, in the latter part of the whole workshop. Then you can get by. That is why I didn't make a presentation. I wanted to make a presentation, but it did not make sense to me. I could come and you just show you 60 slides, and it will be over. But I wanted you to have a sort of like a notes which you can go back to and refer to, because don't feel disheartened if you don't understand every aspect of this whole session. Because quantum inspired optimization, the reason why I'm talking about this is that I want all of you to understand that why are we even studying quantum computing. Like if some of you have interest in this whole field of quantum computing, you already know that the hardware right now is sort of limited, right? We don't have the best quantum hardware right now, and yet quantum computing is such a hot topic. So today, that is the aspect. Keep that in mind. That is what I'm trying to cover today, that why do we even care about quantum computing, even though if we don't have that much of a good hardware. So let's get started now. So yeah, the topic for today is whole session is quantum inspired optimization. So the whole, you can say, even in the whole topic of this whole session, there are 3 terms which I'm using: quantum, inspired, and optimization. So optimization, you guys already know, but although I'll be talking about some aspect of classical optimization, because I need that you can say as a prerequisite before I get into the quantum part. So that is how this whole session will be going. First, I'll be explaining the quantum part. Then why do we even care about inspired? Why not quantum optimization? Why did I even introduce this term inspired? And then we have the whole optimization aspect. Okay, so first of all, let's get into the whole quantum. Let me just write quantum here for now. So when I say quantum, what I'm actually referring to here is that what are the topics, or I mean, I think you already have went through a quantum computing 101. I mean, it was taken by one of my fellow colleagues, and he's a good friend. So I think he must have covered it pretty well. But I'll quickly give you a small glance over, you can say, specifically the topics which I need you to understand as we move ahead in this whole session, or you can say a workshop. So the first one would be superposition. So you guys already know that superposition is basically the property of an, you can say, I wouldn't call it particle, but for the sake of you can say simplicity for me, now let me call it just a particle. For a particle or for a body to exist in multiple states, right? So when I say multiple states, multiple states simultaneously, right? That is what superposition, in simpler term, that is what superposition is. Like, if I say I have this simple coin, a coin can either be heads, a coin can either be tails, as simple as that. So, it has to be either heads or it has to be either tails at once. Now say, I flip this coin, I flip this coin, and now I just close my hand. So at that point until my hand is closed, the coin is in sort of like a superposition of this heads and tails, because it is in a state where it can be heads or it can be tails. It's like a 50-50 chance right now, and until we open our hands, it will be like that. Right. I mean, pretty simple concept. We all. You can. I mean, that is the thing about quantum mechanics and the whole quantum computing. In general, we do things that are related to it, but we don't have the intuition to understand how exactly do we connect it to quantum mechanics or quantum computing. So okay. So I was talking about the coin. So in this particular state, the state of this coin could either be heads or tails, right? But when I'm talking about superposition of this coin, then this would be in a state where it is like, you can say, sort of combined heads tails state, which each you can say existing at a you can say at a certainty of 50%. So this 50%, that is where I want your attention to be. So now I'll move to the actual quantum mechanics aspect. Say I have a quantum particle. Say I have a quantum particle, psi, and already know that the psi can in general have two base states. The quantum, every quantum particle has basically two you can say base states. It could either be 0, it could either be 1, right? So as I said, I'm just for now, I'm just taking for that is why I took this whole coin example so that we can draw the parallels. So now we have this whole you can say a quantum particle. So we are saying that exists in a superposition, right? So as I said, I'm just taking the example of a coin. So it has to be, it has to be in a a way that this is also 50%, this is also 50%. And I expect that after yesterday's session, you already have an idea that this is how we sort of represent every quantum particle, right? Where this alpha square plus beta square is equal to 1. I think you already know that. So if keeping that in mind, it makes sense that any particle superposition is basically 1 by under root 2 0 plus 1 by under root 2 1. There are more states, I mean, now in this particular aspect, you see that the possibility of this, and no, already, I mean, I think you already know that, and when whenever we want to actually find the value of this particle psi or the state in which it exists, we measure it. And just like opening your hand after tossing the coin will have to be in a state of heads or tails. After you open your hand, it cannot be like it's in the middle of the bowl. It will either be heads, it will either be tails, as simple as that. So in a similar way, this you can say is like true randomness. Like like the both of the states have a 50% certainty, right? To to be the output after we measure this particle size. I heard some. Sorry, anyone has any question? Someone unmuted themselves.
No, I think maybe by chance.
Yeah, okay. I'll assume it was a mistake. Okay. So yeah, so I was just saying that now that there's 50% chance of the particle to be after measured to be given output of 0, and 50% chance that it will give an output 1. Okay, so this you can, in some sense, for simplicity's sake, we can assume that this is like a you can say true randomness. We can assume, because if we have a 50, true random nature of a particle to be existing in any of the two particles, then it is like a true you can say it is like true randomness. That is what we'll be using in optimization. And how and why this exactly comes into picture, I'll talk more about it as we move ahead. But for now, this maybe I can talk about it. I think you guys do have an idea. I'll quickly give you a small glance over what exactly I'm talking about. So let me simply say that you already know that any problem has a solution space, right? Very simple. I mean, okay, to put it more formally, I would say that if we have any problem, then there exists, you can say, a possible set of solutions. That is what a solution state looks like, right? So you say, this whole blue thing is just my solution space. Now we want to find, because this is optimization we are talking about, we want to find the most optimal solution, right? And it makes pretty much sense that the most optimal solution will lie within the solution space. Say it's this part. This is where the most optimal solution of the given problem lies. Now there are classically, what would you do? What would you do, right? The first thing which comes into your mind would be brute forcing, right? Try every possible. So okay, just another thing, say there are points within this whole solution space, right? So first possible way would be that I try everything, right? I try this and this, and then I find, okay, now this particular one is the best one I could do. That is classical. That is how we do, that is how we do brute forcing. Now imagine, like, okay, now, okay, just an example, give you very good you can say a metaphor, which I heard from another, you can say one of my fellow colleagues, that classical optimization is like, having a flashlight, like, see, this is my flashlight, right? So a flashlight, the light propagates in a linear direction, you already know that. So this flashlight can only cover this much of an area, like this would be linear in nature, right? Exactly how in this case, after we have done this, then we are doing this. This is linear in nature, right? At one point we are only testing one possible solution, right? Now say I have you can say a lamp. Let me try to draw a lamp. Like, see, this is how, like, we have a lamp here. A lamp, you already know, will propagate light in all 360-degree, all possible directions, right? So this, in this sense, would mean that we are now, you can say, checking a larger space, a larger solution space for the most optimal solution. I mean, if it even if it doesn't make sense, it's okay. As we move ahead, it will. I'll talk more about this particular aspect. Like, this is the whole gist, a crust of why we are even talking about quantum optimization. So to put it, put it into a single line or one line, what I'm exactly talking about here is that by having quantum superposition, we are able to test more of a solution space at a single I will not call it iteration, but at a single unit time. I'll call it unit time here for obvious reasons, because if I try to so, I mean, this would be a bit technical, but I mean, for those who want to have a deeper knowledge, this is important. You already have the concept of time evolution, right? We talk about time evolution in quantum mechanics, and not like this whole stepwise thing, because we cannot discretize every time. The whole quantum mechanics. The quantum mechanics is not your classical everyday science or everyday physics. It is a bit different. So I mean, honestly, just going a bit off track. So the whole the difficulty of this whole quantum mechanics and computing is not it's mathematics, and it's not how hard, how big theories it gets. The actual difficulty, and why quantum computing is considered to be hard, is you have to have a different intuition. When you come into this domain, when you come into this workshop, you're not expected to you can say have a very good grasp, you can say, I would say, like, keep your in your mind the classical aspects. The classical aspects are still there, right? But we are sort of turning them into a way that it might not make sense. Like, this particular aspect which I just talked about, that we talk about time evolution and not like discretized episodes of events. This might not seem very intuitive, but once you start spending time on this whole aspect, it will start to make sense. So just a small advice, whenever you come to any quantum computing session, expect some weird keywords, or you can say weird statements made by the speaker. Okay, so that was more or less about superposition. Then I'll come to entanglement. Entanglement is like, it's not that much used, honestly, but still, for certain algorithms it plays an important role. I mean, I'll not be discussing the entanglement aspect in depth, because the entanglement itself is a very, I would say, confusing topic. Like, it's easy to understand but difficult to explain. So anyway, so you already have an idea that entanglement is nothing but, say, I have this particle P1, I have this particle P2. These two particles are somehow, I would say, associated with each other, such that if I say I measure some property small p1 of this particle p1, then somehow I'm able to predict this you can say the property small p2 of this particle p2 as well. It's as simple as that. So how does entanglement come into picture into this whole optimization aspect? Well, as I talk, we already are familiar about solution space, right? So from the solution space, say, I have some x star, a candidate solution, say, something 0 1 dot 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 0. This is like a candidate solution to some binary problem. For simple, let's assume that. So like this is say 1, and this is some other solution 1 0 dot 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 0. These are like candidates. This might be the best solution, or this might not be the best solution. This is the candidate for being the best solution, right? So say these are two possible candidates which I have right now. So how entanglement will help me here is that, say, there might be an, say, this okay, this is very problem specific. So this is not a general statement which I'll be making now, that some problems sometimes can have multiple candidate solutions which are related with each other. Say for some reason this solution, this x1 star, is related to this x2 star, right? This I mean, I would say a good example would be a knapsack problem, in which your previous solution, say in which, say you already know, like if you are from a computer science background, we already know that a knapsack is like a best possible, you can say, for some simplicity, let me call a best possible combination of you can say state, a best possible combination of state, right? So there might be a possibility that in problems like knapsack, there is an association between one candidate solution and the second candidate solution. In such situations, entanglement comes in very handy. There are algorithms, like there is this whole algorithm. I mean, I won't be covering it today, but if you're interested, I would say to actually look into it. Quantum teacher children learning algorithm, children learning algorithm. So what I'll give you a quick gist of what it talks about is, so there's a classical teacher learning algorithm as well. So what the concept basically is, like, say, okay, a very good I got a very good metaphor to explain this thing to you. So in a class, there is one topper. I mean, okay, there is one topper and other are, average students. Assume that. So during just before the exams, the average student just surround the topper and to get more and more knowledge out of him. That please tell me that, please explain me this and that. So that topper is like the leader, and all others are sort of like learning from that leader, right? And after, say, this was first semester scenario, right? They say after second scenario, some other student tops, then that student becomes the topper, and so sorry, the leader. So you get the gist, right? So in every iteration we have a leader, and other you can say other particles, I would say, or other states are somehow learning from that leader state, right? So that is what teacher learning is. So in this, you get a gist, right? In this particular algorithm, there is a relation between each state from like p say if this was the leader, and this p1, p2, and p3 were all, you can say, children, I would say. That is, these are called children. So if there is a association between this p1, p2, and this p1, p3, and this p3, p2, right? So in this particular algorithm, quantum entanglement is like, see, another thing, because as I said, I'm talking about inspired algorithms here. So you don't actually put these things in a quantum computer and entangle particles. You simulate entanglement, you simulate the properties of entanglement. So yeah, this is one of an example where entanglement actually comes into play. And now another important algorithm, this particular property is, you can say, is the most important, and I would say it's the simplest to understand, and why this would be important. Interference, actually. Interference. So interference, exactly what it means in classical physics. There are two types of interference, right? We have the concept of constructive and destructive. Right? So I don't think, I mean, but when I do quantum computing 101, honestly, I play a very you can say strong emphasis of interference. So because I did not attend the Mondays or Tuesdays workshop, so I'll quickly give you a glance of what interference, what do you mean. So say you have this particle psi1, it's some wave, say this is the wave, and say if I have some particle psi2, it is also a wave. Say this is a smaller wave, but more frequency. So say if I combine, if I say I put psi1 plus psi2, so you see that both there will be constructive criticism, interference. I'm like, this is not like exactly what I mean. I'm just trying to get the gist. So they might be constructive and both destructive in this case, but for now I'm just assuming that there's only constructive interference. So the wave produced will be like this, right? And the destructive opposite of this, right? The time, basically maybe the wave is are inverted, like the wave, the crest and throws are inverted, then there will be destructive and the amplitude will decrease. Simple, very simple concept. We already know these things from classical physics. So what here in quantum, why I'm talking about this is, like, see, any particle, any quantum part any quantum particles, I won't say, which is just alpha 0 plus beta 1, and say I have this side 2, which is alpha 0 plus beta 1. Let me just put it 1 1 2 2. Now say you already know that these size are nothing but yeah, I already talked about the whole measurement aspect, right? Say after I measure this particle psi, it will give me either a 0 or 1, right? As I said, like a coin flip, once you open your hand, it has to be on heads or tails, right? It cannot be in a state where it's between heads and tails. And similarly, so yeah, and so you're similarly inside to also it has to be in either 0 or it has to be in either 1, right? Now the important aspect here is that I think in quantum computing 101 you must have known, how do we know that what will be the output when we measure psi 1 or when we measure psi 2? That is where the concept of probability comes in. I already said this, so I'll just repeat it, that this alpha square plus beta square is equal to 1. This is very simple. If you can get grasp it, you already know what I'm going to talk about. This is simple basic probability. So basically, the square of this you can the coefficient that I'm putting before the state, that the square of the that amplitude, that is basically amplitude in terms of wave. Let me just draw the pic that will help you out. So this basically this amplitude. Basically, I mean, this is one dimensional, but I'm talking about 2 dimensions, so the wave would be as simple as that. But the square of this alpha, or the square of this beta, that will determine that after on measurement what will be the output. So as we already see that in case of for superposition, it is 1 by under root 2, and the square of 1 by under root 2 is 1 by 2, which is 50%, right? So now you get the gist that say for the sake of this example, this was my initial state I, and this was my solution state, right? So the whole objective of our whole optimization is to go from I to S, right? Very simple, like we have to go from initial state to a solution state. And how exactly can we do that? We already know that once we measure this I, it will be either 0 or 1, right? But before we have measured it, that is where we do everything in quantum computing. Yeah, this is important that understand this, that like, see, the whole quantum computing has basically 3 steps. We initialize our qubits. We start with a 0, initialize this to some state psi. We perform some operations, which are like quantum gates, which I think you already are familiar with from yesterday's session, operations, and then we measure. So this is where the whole magic happens, because once we have measured, then it is just basic classical 0 or 1. I mean, it's wrong to say that it's 0, it's actually this, but for simplicity's sake, we can say like it is 0 and this is equivalent to 1, right? So this is where the whole magic hides. This is where the whole quantum actually happens. So now it would make sense that when we are talking about that quantum part, what exactly are we talking about is to change these coefficients, right? Because these coefficients determine what happens after measurement. For example, for initially, say I have alpha is equal to root 3 by 2 and beta is equal to whatever, you subtract by square, you get whatever the beta will be. Then we have to change this alpha and beta so that let me just say for simplicity's sake, it says it's 1 by under root 2 and this is also 1 by under root 2. So right now it's in a 50-50 state. You don't know what will the output will be. It's by equal probability, it can be 0, it can be 1. But now in actuality, in reality, say for simple example, say the solution answer, the answer to a problem is 1, but you started with I as I think you already, I should have used this notation. I think you already are familiar. This is like the superposition. This is like the symbol, I would say notation for this particular state. Yeah. So now your goal, or the goal for you now is to take that 1 by under root 2 to basically close to 1, because you want as close as possible. You want the probability of it being 1, to be as close as 1. It has to be in ideal situation. You will try to make alpha to be 0 and beta to be 1, because you want 100% of times to be to be the solution state to give an output as 1. But that usually does not happen. So okay, now keeping that in mind, so you already have an idea that what we are trying to do here in the quantum layer, where the whole magic happens. We are trying to change these alphas and betas in such that after measurement of a solution state where we have changed the alphas and betas, we land more on the solution state, right? So that is the whole.
Abhigyan?
Yeah, please.
Yeah. Just wanted to say, like, alpha and beta, they are like the parameters that we are trying to optimize so that we are move close to the solution.
Yeah, you can say, in some sense, yes. But see, actually, in actuality, okay, that's a very good question. So, it might seem that, we are trying to optimize basically alpha and beta, but that's actually not the case. So, say, if we have function, if we have, let's say, function fx, that is what we are trying to optimize, say, for example, then this x, for example, say, is a bit string for now, is a bit string. So we are trying to find the best possible bit string, x1, x2, ... xn, right? But this particular, say, this whole bit string, if we divide every or you can say bit of this bit string, that is a qubit in our case, right? So there's say for example, if the best possible, I'll assume that the best possible answer was 1010. So this would be qubit 1, this would be qubit 2, this would be qubit 3, and so on, qubit 4. Now what I'm trying to sort of build the intuition that what happens behind the picture, so that all in reality what we are only concerned about is to get the best, to get the q1 to be 1 and the q2 to be 0 and so on. But what happens in the background is that once we start applying gates, we'll see that how exactly do we you can say implement the whole optimization aspect, how exactly do we modulate these values, right? So just to clarify it, we are not trying to find the best possible value for alpha and beta. The alpha and beta will change automatically. It's like best possible example I could give you is like if you I mean, in machine learning we talk about hyperparameter tuning, right? We tune certain parameters and we get a you can say a certain output, the adequate output, right? In our case, yeah.
Again, I think we are trying to reach towards, from our initial state, we are trying to reach to our final state early by changing these alpha and beta values. As do I feel like we are not changing alpha beta. Psi1 is our initial state, and at each and every step we are changing our state, right? At each and every step we are changing our state. And for changing our state, definitely our state depends on alpha and beta.
Exactly. So
right.
So I'm talking about what happening in the background. Actually, we are not concerned. We won't be actually trying calculating the value of alphas and betas. That whole thing will happen automatically. Like it's like saying that in gradient descent, we don't actually the slope thing that happens in the background. We are only concerned that how the value drops and what value of delta we get. That is why we are only concerned about this value of psi2. What the alpha and betas are in the background, we are not concerned about it. But just to build an intuition that what is happening behind the curtains in the black box, what is happening within this whole quantum, the way how the whole quantum magic is happening, that's actually we are just trying to we are modulating the values of alphas and betas so that on measurement we are close to the solution state. In you can say in ideal situation it will be 100% of times that we get psi or psi2, but that's not actually the case. We will not be like it will never be 100%. There will always be some randomness. It will be like that alpha is 0, beta is 1. It will be 0.3 and it will be 0.7. something along those lines.
So like just
once again, that what is happening like behind the curtains that you were explaining about alpha and beta.
So, okay, I mean, okay, first of all, like we are only concerned, like, you know, our problem lies in finding this side 2, which is the solution state. That is what we are trying to do here, right? So any, I mean, for simplicity's sake, call me this like this is side 2, a particular qubit of this whole bit string. That is what we are trying to do. But how do we get there is by changing these alphas and betas. And how do we change these alphas and betas? We have quantum gates for it. Like, you know, for say, you know, I have this whole block, I mean, you guys, I mean, you already are aware of the concept of block sphere, right? So say, you know, if this is 0 and this is 1, so what I'm trying to do here is that I'm trying to change this arrow in such a way that on measurement, it is more likely, assuming that the solution is 1, it is more likely to give me a 1. So, I mean, you do, and I mean, how do I put it again? So
it's
what?
same like we can I interrupt please?
Yeah, yeah, sure.
Same like as we were having as we take any optimization algorithm like PSO. So in that we are having like we are having two factors. One is like that's taking it towards one is like our volume, right? So we are taking it towards our right state, towards our best solution. So that
Exactly.
same we are trying to do here through our alpha and beta. Those
Yep.
are our quantum coefficient.
Yep.
And this circle sort of which you made, it's like you're talking about, that's our search space, which
Yes.
will be in between 0 to 1. Fine.
No.
Which,
Yeah,
no.
that then sorry, that is not a search space. The search
Okay.
space is still this bit string. You know, the search space is still this
Okay.
W1, W2, W3.
Right.
That is a search space. Like, you know, if this is, say, you know, if this was if for the 3-bit problem, if the bit string length was 2 to the power 3, then my search space is still 2 to the power 3.
Okay.
Okay.
But each and every bit is between 0 to 1.
Exactly.
Right.
So yeah, I mean, okay, so I mean, see, if you're not, I'll talk, I wanted to cover it later, but okay, just because we're talking about it, it's important that I clarify this, because it will, you know, build up to be. So in actuality, the what's happening, so okay, I'll take a very simple example, you know, of genetic algorithm. I'm going to talk about it more, but I'll give you a very quick overview. So you already know that the whole step of this genetic algorithm is that we initialize the population, right? And then we, you know, perform, for now, say, you know, we pass it through some fitness function. This is the first one, of course. So then we perform, you can say, crossover. Then we have the mutation. And depending upon, you know, how, you know, we performed on the, you can say, the fitness function, there will be some selected and there will be some rejected. And then in the, you can say, from the selected one, we perform the crossover. I should have made it in a different way, but say, you know, I'm writing it here, we are performing crossover with the selected one. And then we perform mutation, and then we get the new population. So this is like the classical sort of very basic classical genetic algorithm. So now the whole quantum actually comes, how quantum comes into picture is, the first time we initialize the population, what we do is, if you know, this is a Hadamard gate, and Hadamard gate basically puts any qubit to superposition meaning that it's in a state where both is 50-50. So we start by that. So once we are started with a state that is like in a superposition, that is like, you know, it's in the 50-50 state, you know, that right now we are here. When this is 0, this is 1. So it has equal probability of being 0 or 1. Now we measure. As I said, this is like true random. So the first population we get after this is truly random. So this will be truly random. Okay. Now, yeah.
May I ask one question?
Yeah,
how
please.
do we decide these gates that we have to apply these gates? Like in this case, we are applying Hadamard gate.
Hadamard gate, yeah.
कभी हम XOR कर रहे हैं या NOR गेट, so how do we decide this?
यहाँ पे इम्पोर्टेंट ये है मैम कि फर्स्ट टाइम अब जेनेटिक एल्गोरिथम क्लासिकली भी अगर इफ यू टेक इट, तो फर्स्ट इटरेशन में आप क्या चाहोगे, यू वुड वांट कि सारी पॉपुलेशन रैंडम हो, राइट? बिकॉज तब हमको वी हैव नो आइडिया कि सोल्यूशन कहाँ लाई करता है, राइट मैम? सो हैडमार्ट गेट से हमको जो स्टेट मिलता है वो, अगर मैं सिंपली ये 0 को पास करता हूँ तो मेरे को मिलता है 1/√2 0 + 1/, तो ये कंप्लीटली रैंडम है. If I were to measure it, ma'am, तो 1/2 की probability set could be 0 or 1, तो 50-50 chances है, तो that is completely random. तो that is what we ये first Hadamard के लिए. अब इसके बाद ना मैम we don't apply any specific, okay, we'll continue. तो this is truly random now, right? Now what I'll do is I'll pass every possible, say I have 10 candidates, right? अब मैं 10 candidates को I'll pass through this fitness function and I'll trace a threshold, like मैंने अगर threshold θ1 रखा, तो अब जो पास कर गए थ्रेशोल्ड को, I'll keep that in selected and I'll keep the rest in rejected. Okay, now what I'll do is कि जो selected थे उनमें तो मतलब I'll perform the classical crossover, no issue, this whole thing is still classical, but I'll determine कि how many of my population, how many of the my you can say out of 10 only 6 got selected and 4 got rejected, right? And in this 6 I perform, for simplicity alpha now, because okay, I find a value of delta, that is determined by how close these were, how close these were to the threshold. How, in this case, because if I try to minimize it, depending, like it could be a minimization problem, it could be a maximization problem. For now, say we have minimization problem. So out of these 6 selected solution, the one that was minimum, right? From the value of alpha, from the value of alpha and beta, I still have that alpha and beta, right? How do I change this? Is now there comes the concept of delta. This delta I'll determine using my 6 solution states, and I use this delta. Now what? Okay, now what? I'll quickly draw a quantum circuit. Actually, that will help you to understand. I have this RX gate here.
अभिज्ञान, एक सिंपल सा एग्जांपल ये भी बताओ कि how मतलब choose the fitness function for a simple problem, like you have worked on the genetic project. एक fitness function हम कैसे through gate decide करेंगे?
हाँ ठीक है, I'll make sure I'll quickly go over that. But जैसे यहाँ पे केस में जो this RX gate basically what it is, I mean RX gate I don't think cover किया होगा. I mean X gate तो you guys would have covered, right? X gate flip करता है 180 डिग्री along the X axis. मतलब अगर मेरा ये होता है 0 और ये होता है मेरा 1, तो X gate इसको flip करके 1 कर देता है, right? अब मैं क्या करूंगा, RX gate एक parametric X gate है. अब parametric in sense that अब how many degree do I want to change this, how to, okay, like this, if this was 0, how many degree do I want to rotate it to go down? You see, I mean, now it should make sense to you. When I'm doing this, what I'm actually doing is I'm changing the value of alpha and beta. Okay. Yes. So as I'm going down, तो alpha decrease हो रहा है, beta बढ़ता जा रहा है. At a certain point, दोनों 0.5 फिर से होंगे, and then beta will keep on increasing, and alpha will keep on decreasing. So in actuality, alpha and beta are determined by the performance of your previous state. मतलब अगर मैं इसको ऐसे बोलता हूँ, अगर psi I है तो psi I + 1 है, तो how will psi I performed, उस हिसाब से psi I + 1 बनेगा. तो बैकग्राउंड में अल्फा एंड बीटा चेंजेस हो रहे हैं, लेकिन हमको सिर्फ दिखता है कि psi और ये psi I का क्या आउटपुट आया और psi I + 1 का क्या आउटपुट आया.
क्योंकि psi is combination of alpha beta
exactly.
with gate combination.
Exactly. We don't know what alpha and beta are. We can never know. That is a mystery of quantum computing. क्योंकि एक मतलब just थोड़ा off topic, then I'll come to a fitness function thing, कि there is a theorem in quantum computing, no cloning theorem. वो ये कहता है cloning theorem, no cloning theorem. अगर मेरे पास एक पार्टिकल अल्फा 0 है और एक उसका बीटा 1 है, even if I tell you ये psi 1, you can never recreate this psi 1. You can never create a copy of this psi 1. Because there's no way of determining what alpha and beta are in actuality. You can never determine what alpha and beta are. You can only, in actuality you can only measure the state, right? Agar main bolta hu ki if I give this you psi, then the first thing you'll do is I'll measure this. So once you measure it, it will either be 0, it will either be 1, and once you do that, this alpha and beta information is lost forever. So there is no way of knowing alpha and beta, and hence why there is no way of making a copy of a state. So the best you can do is like somehow, if I tell you the process of how I created the state, like मैंने start किया 0 से, फिर मैंने x gate लगाया, फिर मैंने Hadamard gate लगाया, and that is how I got to this minus state. Then maybe you can recreate it, but you can never make a copy of my state. So this is important. अब now talking about a fitness function thing. So actually, मैम fitness function इसमें quantum का उतना role नहीं होता मैम. It depends upon the kind of problem. Like there are, you can say, multiple kind of problem. Like I'll send you an article. Actually, I actually wrote an article on it, so I'll send you that. But to give you a gist, मतलब there are like multiple things. सबसे पहले तो just say I'm not good at drawing, so I'll still try. But so if this is my function, this is smooth, right? Then the fitness function for this would be pretty simple. You can have a linear 3-dimensional function that will pretty much have a smooth slope, so वो काम कर देगा मैम आपका. And then you have a structure rigged, मतलब अगर यही चीज ऐसे जा रहा होता है, ऐसे 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 पीछे, then इसके लिए fitness function में you'll have to consider कि इस पे कितने सारे local optima, मतलब ये भी local optima है, ये भी local minima है, ये भी है, तो उन सब पे मैम determine होगा. तो फिटनेस फंक्शन तो मैं कंप्लीटली यू कैन से प्रॉब्लम डिपेंडेंट हो जाएगा, कंप्लीटली प्रॉब्लम डिपेंडेंट हो जाएगा. बट व्हाट यू कैन डू हियर इज, इसमें एक चीज इंपॉर्टेंट व्हाट यू कैन डू इज, इफ यू कैन समहाउ कन्वर्ट योर फिटनेस फंक्शन into something that works pretty well with quantum. Like abhi tak ma'am, if we have talked so far ki we have this alpha and beta, that is one way of seeing things. Another way would be ki because this whole aspect we are talking about gates, right? कि हमारे पास x gate है, y gate है, हम x के पैरामीटर्स चेंज करके उसको इस हिसाब से कर दे कि वो कुछ पर्टिकुलर एंगल पे रोटेट करे, कुछ इस पे करे. अब we already know, I think you already know कि गेट बेस्ड के अलावा भी there are more architectures. There are quantum annealing, there is photonic, quantum photonics, and so on. So quantum annealing में there is a concept of QCA. उसमें what you can do is आप अपने fitness function को you can look it up. I mean, for the sake of time, I have to get back to my schedule वाला thing, but then I won't be able to cover certain stuff. So or maybe I can try to cover it at the end. Maybe I'll try to do it. If possible, I'll try to do it. So QCA में what you can do is you can take your fitness function, मतलब major fitness function. I mean, for simplicity's sake, let me say sin 3x was my simple fitness function, and now you can convert it into a form जहाँ पे it will be A, and there are certain terms within it. This is Hamiltonian, and B, A by 2, it is A by 2, and B by 2, and certain Hamiltonian. If you can convert your problem into this form, then so you can solve it on a different architecture. It's quantum annealing architecture. That is better. I'll talk more about it, how quantum annealing is different from normal annealing and all that stuff. So yeah, for now let's keep it on a hold. I'll keep it on a hold. If there is time, I'll explain QCA. QCA, I'll just give the full form is, it's basically quadratic unconstrained binary optimization. Okay, so interference ka to quickly sum it up, interference mein what I was trying to tell you is कि हम लोग we are still working with the states psi1 and psi2. वो कहीं नहीं गया. हमारा अभी भी solution state will still just be a state psi2, जिसको हम जब measure करते हैं तो वो हमको एक bit की value देता है 1 या 0, as simple as that. But background में हम एक्चुअली क्या चेंज कर रहे हैं, मतलब हम करना क्या चेंज जा रहे हैं, अल्फा बीटा पे साई की डिपेंडेंसी अल्फा बीटा पे है, और हमारे सॉल्यूशन स्टेट की डिपेंडेंसी साई पे है. तो ये ऐसे जाता है, मतलब ये जो डिटरमाइन करते हैं साई 2 को, और ये डिटरमाइन करता है 0 होता है कि 0 होगा कि 1, ये डिटरमाइन इससे होता है. और इससे फिर हमारा पूरा बिट स्ट्रिंग बनती है, जो कि इंटीजर हो सकती है या सिंपली बिट वैल्यू हो सकती है, सो ऑन. तो हाँ, अब
Abhigyan, एक मिनट, just
Yes,
you
ma'am.
have
Yes,
given
ma'am.
one, just come on your top of, just scroll your screen, please. Yeah, this last line which you have written about QCA, what was
QCA.
that? Just explain that, please. This
Okay.
not QCA, this is 0, and then you are transferring that to X, and then
okay.
add, what was that you were explaining there?
This one?
No. That just about that, you were saying that initially we applied. You were saying that initial state was 0. Then you have applied XOR
Okay.
gate, and then you said that you have applied Hadamard gate. So what you were explaining there?
Okay.
Please,
So okay, let me.
yeah.
Now I'll draw the full
Yeah.
circuit now for this whole genetic
Yeah, please.
algorithm.
Yeah, please.
So that would. So yeah, if you understand one algorithm, you'll understand every algorithm. That is also a good way of explaining it. Okay. So we start with say 0. We have say 10 qubits. I have 10 qubits, and we all start with 0. Okay. Start in the genetic algorithm, the very first step in classical, even in classical, is to generate you can say random population, most random, as much random you can get. So what I do initially is I put a Hadamard gate here. In all 10 qubits I put a Hadamard gate, right? I measure it, right? This whole thing I do it for say I have this is the gene length. Actually this is one gene. This is one chromosome, actually one chromosome. Say I have and every qubit is a gene, like simple, just talking about the genetic algorithm. Now say if my population is say 100, right? So I'll run this circuit 100 times. Okay.
Right.
And say and you know after measurement we'll either get 0 or we'll either get 1. So you say I get this the 10 length, so I guess this, I get dot this, and so on 100 times, right?
Right.
So this is my first step. This is population generation.
Yes.
Right. Now I'm talking about how we are going to change the next. So this was first, right? We'll just do we'll have some selected, and we have multiple methods. In crossovers we can do tournament selection, right? We can do binary selection, so on. So say for simplicity's sake, I'm doing tournament selection. So out of this, say this one wins, and then this one wins, and so on. Say we have 50% of population which isn't selected, and 50% which is non-selected, discarded. Okay. Now say in because I'm taking 100 as an example, the 50 which are in selected unme se depending how many were you can say I'll take any I do this first because this is important. So you see that I told you that every single qubit is a gene of a chromosome, right? So what I'll do is I'll see for a, say I basically do this. This will simplify it. I'll do this. This is psi1, this is psi2, and so on. This is psi10. Considering कि मैं इन qubits को भी psi1 और psi10 बोल रहा हूँ. Okay, this is making sense, right? मैं कुछ नहीं किया, मैं कह रहा हूँ कि ये अगर ये वाला सर्किट मेरा एक क्रोमोसोम बनाता है, तो उसका क्रोमोसोम का एक क्यूबिट एक जीन होता है, राइट? Now what I'm doing is मैं एक सब क्रोमोसोम्स के फर्स्ट जीन मतलब फर्स्ट क्यूबिट को देखता हूँ, okay, and I determine how many number of times I get 1 and how many number of times I get 0. Okay, depending on this I have a formula which calculates delta. Delta क्या है? This delta is now this was my first circuit. ये सिर्फ एक ही बार रन करता है, इसके बाद we don't use it. Now we use the second circuit. We again start with 0, but instead of Hadamard, now we have a RX gate.
So Abhigyan, on every qubit of every chromosome we are testing this delta.
Yeah, this delta, I'll tell you this delta. That's what I'm saying. So this RX, what is
delta is our function, which is like minimization or maximization problem.
No. That is fx. So
this is deviation, no?
Yeah,
deviation from the solution space.
This you can call it deviation, but not exactly. This delta is basically what gets added in this RX. Actually, I'll tell you. So you already know about X gate, right? So X gate, what it does is ये 180 degree पे rotate करता है. तो like अगर यहाँ पे था तो वो यहाँ ले आएगा and vice versa. Right. Now what I want is मैं पूरा rotation नहीं चाहता, मैं कहीं middle में जाता हूँ कुछ angle theta से. Okay. तो this delta will help in determine this theta. Okay. So by using this delta, I'll determine what parameters I pass into this RX gate. मतलब कितने डिग्री से भी I want it to rotate along the x-axis. इससे what I'm doing is इससे आई एम चेंजिंग द प्रोबेबिलिटी कि मेरा ये वाला क्यूबिट 0 होगा कि 1 होगा. अगर से first say if I rotate only, if I rotate by say 30 degree, so it will still be more than 0.5, right? 30 degree ka, you can find you can say the cos of 30, it's still you can say root 3 by 2, which is still 3 by 2. So it will still be along this line, more than 0.5. So it is still more likely on measurement to give me 0, right? And same
delta is, I think, as Shubham said, it's, I think, deviation only. This is taking our solution towards best.
yes,
Like we are changing degree to take it fast towards best.
Exactly.
So
That's
I think we can call it deviation only. In technical term, what you call, I know that I don't know, but I think this
for
is
the sake of our understanding, like we are.
Yeah. So you can say, yeah. I mean, as we move ahead, as the number they will, this delta will keep on decreasing, right? And after a certain point, there will be no change. Same gender population banta jayega.
Right.
So yeah, you can call it delta in some sense. Yeah, that it is delta. But the thing that why was not you can say not using the term delta, because kyunki I'm talking about quantum here. So what theta mein add hota hai delta. So that is why I was referring to it. But okay. So now I will, what new state I'll get is, यहाँ पे I'll be more closer to the solution state depending मेरा पहले क्या solution आया था, and that's it. Now I'll get a new population 0 1 1 0 dot 1 0 0 0, and फिर से I'll repeat it. फिर से I'll just check कि इस particular gene पे कितनी बार 0 कितनी बार 1 आया. ये selected, this I'm doing only for selected. Discarded तो discard हो गया, उनको I don't care about them. Okay, so this circuit I'll run as many times as I said. There's two way. Like one thing I could set a threshold. Ki iska out of the selected one, the one that performs best. Let's say this was the best one. If this you can say is below a threshold, there are two threshold. One is जो determine करता है कि वो winner है कि loser है, and second is कि वो कितना accurate solution चाहिए. Like say if a function fx that has minima at 0. तो funny thing here is that this I'm talking from experience, 0 कभी नहीं आने वाला, because machine 0 और 0 में difference होता है. तो machine 0 is about 0.0 ... e something minus plus something. तो हम लोग वहां तक नहीं जाना चाहते हैं. We said कि अगर 0.0001 से कम हो जाए वैल्यू, बस स्टॉप कर दो एल्गोरिथम को, क्योंकि वो हम 0 मान लेते हैं कि हाँ वो 0 हो गया. तो उसी तरीके से या तो ये दिस इज वन वे कि हम लोग एक थ्रेशोल्ड सेट कर दें कि व्हेन द बेस्ट फंक्शन, बेस्ट क्रोमोसोम का फिटनेस इससे कम हो जाए, एल्गोरिथम स्टॉप कर दो, खत्म. अदरवाइज what you can do is कि just set a number of iterations कि 100 times मतलब ये वाला स्टेप रिपीट करो, जितने भी आए fx की वैल्यू, मतलब क्रोमोसोम और उसका मिनिमम वैल्यू, वो रिटर्न कर दो. सो ये this whole was just a genetic algorithm using quantum. अब इसमें because इसके through I can explain why I was talking about inspired thing. So in actuality, if I were to do this on a real quantum computer, so I'll use a term. This is very important that I mentioned this term NISC. If you're ever going to work on a quantum computer, then it's important that you understand this. So right now, when starting, so I've been saying this. Although we live in an era where the quantum computers are not that well built right now, we still talk about quantum computing. It's still a very hot topic. So like this NISC era, this is like NISC, and this is the era which we are living in. This is noise intermediate scale quantum. This means is that like a quantum computer which we have right now are noisy. Noisy means they are very prone to external stimuli. Like if I make a qubit, you already know that this is what a qubit looks like, right? So I'll set some properties, right? I'll set some properties alpha and beta, but it will not stay like this. If I keep this psi1 in a space for 1 second, it will somehow change to some alpha 1 0 to and a beta 1. This is noise. And there will be, I think there will be a session on error correction. Usme they'll talk about noise and how we correct this noise. We can correct this noise, but not to a point jahan pe the qubit are usable. And second, scalable. The quantum computer right now are not that scalable. Maximum we can do right now is about 120 qubits. And 120 qubits, I'm talking about, for my, say, if I were to do my genetic algorithm on a real quantum computer, so maximum I can do is 1 to the power 120 states wala problem. This might seem a lot. Matlab, general function, matlab, simple. If I'm just doing this, if I only want to optimize fx is equal to sine x, then to it's sine 3x, then to it's very more than enough. I don't even need 120. I can do only in 5 qubits. But now when I'm talking about industrial problem, the type of problem which, like my company or any companies work on, those require much billions and trillions of, states. Usme it fails. Plus, it is very slow. Quantum computer right now, unko access karna and get a solution, that is slow. So that is exactly why I'm talking here on quantum inspired algorithm. So instead of actually, passing it through a gate, so I think, जिसमें that कल, I think yesterday, I think ये हुआ होगा कि सारे जितने भी हमने gates अभी तक mention किए, those are nothing but matrices, right? मतलब इसको मैं चाहूँ तो 1 0 नहीं, 0 1 1 0. X gate ko I can write this like for a 2 qubit system. I can simply write it like this. So you already know कि इसका क्या मतलब होता है कि if I like multiply this with 0 1 1 0, so what I get is 1 0, which is nothing but 1, and we started with 0. ये tensor product होता है, like not like actual multiplication. This is tensor product. So we already know this. So if you can sense that we can simulate quantum computer on your local machine. कर क्या रहे हैं हम लोग basically even in this whole circuit thing, we are just doing multiplication. We only have a single gate and we start with 0, right? So basically what we are doing in this whole aspect is we are starting with some big matrix 0 dot 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 1, something like that, which is like my state psi1. हम इसको मल्टीप्लाई कर रहे हैं एक और मैट्रिक्स के साथ, दैट इज लाइक द आरएक्स मैट्रिक्स का गेट. इट्स इसका मतलब इसका जो nth फॉर्म होता है थोड़ा कॉम्प्लिकेटेड, आई एम नॉट टॉकिंग अबाउट इट, बट से इट इज अ मैट्रिक्स जो n by n ऑर्डर का है, गिवन दैट कि ये n by 1 का मैट्रिक्स है, तो हमको एक फिर से n by 1 का मैट्रिक्स मिल रहा है. दैट इज एग्जैक्टली व्हाट वी आर डूइंग इन सम सेंस. तो why don't we simulate our whole quantum computer on a classical machine, considering कि हमारे पास insufficient memory है. मतलब there are good libraries out there. There are NumPy libraries out there. There are, you can say more parallel algorithm which can do multiplication much faster on a classical computer. Then why don't we use it? So that is exactly what we,
I think because quantum giving us that multiple state and simultaneously it can run, that's why we are using quantum instead of classical one.
Yeah. That is what I'm trying to make a point, ma'am. Ki these algorithms, these are quantum ready algorithms. As soon as until you have a problem जो कि आपका quantum computer के तक scale हो सकता है. मतलब if I only need 10 qubits, then तो I will just basically I'll use the same concept. Change कुछ नहीं करूँगा, ma'am. I'll run this thing on a quantum computer. But for example, if you want to solve a problem जिसमें you'll need 1000 qubits, it won't make sense क्योंकि आपको मिलेगा ही नहीं इतना बड़ा quantum computer. Then you can simulate on it on a quantum, on a classical machine. That is where the concept of inspired comes in, which means here
I have two doubts, please.
Yeah, ma'am, please.
Related to this only.
Yeah,
one is like when we talk about any neural, or we could talk about, then state is changing according to SGD, gradient descent. It's coming down. If it's far, it's dropping its slope according to trying to come to best state as fast as possible through SGD. Then when we talk about optimization, fine. Then we take any algorithm. In any algorithm, either if we are taking genetic or if we are taking PSO, then changing its chromosome. Again, concept is like it's taking that towards best solution as fast as possible, as was in SGD also.
Exactly.
So these two. Now, when we are talking about third, that is like quantum. Fine. Quantum is not giving us any sort of algorithm. Whatever states we have, it's just running those states fast because it's running simultaneously.
Exactly.
No concept like towards taking it towards best no concept like that in quantum. That's why you are using inspired, and even we can say quantum neural network also in future, or maybe these terms already are in light. I don't know about that. Yeah. So that is like, because we are not having in quantum, if we can run 2 to the power something, but that will run fast on quantum computer as compared to any other server. Right. So, but there was one more concept in quantum, that was entanglement. Entanglement was combining particle so that it should not run on all state, all 2 to the power 10 or all 2 to the power 15 state. It should not run all, it should run some to go towards best. That's why we were having entanglement on quantum.
Exactly.
Then I think optimization already given by quantum. Well, this is like, maybe I'm new to this and this is like my thought process. Just I would like to know, is it should not be something like we are unnecessarily going for inspired, already quantum giving us inspired through entanglement. That's why that is my concept.
Yeah, I got your point. And yeah, let me tell you a few things. So yeah, you are absolutely right. There are quantum optimization algorithms. So okay, now I'll quickly, I think it's a good, it's a good thing you brought it up. I'll cover another topic. So I was going to cover it anyway, but I'll cover it now. Quantum annealing. So I think, from physics, those who come from physics background already are aware about this term annealing, right? Annealing is very simple. Just to put it more simply, it's like, it's come from thermodynamics actually. Like, you already know that every body tends to be in a state of minimum energy. It will try to be in a state of minimum energy. The universe is always dissipating energy to be in a state of minimal energy. Very simple concept. So we and also in metallurgy we talk about annealing. This concept. So okay, now just not getting off topic. So annealing, is annealing in this particular aspect, it's a stochastic optimization algorithm, by the way. So we say, if we have this kind of if this is this kind of landscape, this is like fx and x. So in classical simulated annealing, what we do is, or in thermal annealing, whatever you call it, like I'll call it classical annealing for now, not getting into integrity details. We start from some random state, say here. We check the neighbors. This particle will check its neighbor, this neighbor, and it will keep on going. It will keep on going. So it is random, it is stochastic in nature. So there is randomness associated with it. So it will slowly get here, or it can go there, whatever. So now, for the sake of this example, say, we started from here, right? And we already know that this is the global minima, right? So in classical annealing, what we expect are, you can say, the annealing algorithm is to perform a thermal jump. Thermal jump is basically like it will go from here to here. We expect algorithm to do this, right? So this is computationally expensive. It looks and it will be expensive. In quantum annealing, there is a concept of quantum tunneling. So quantum tunneling, what quantum tunneling is this is interesting, and I'll talk about quantum tunneling a bit. So quantum tunneling, actually, you have heard about this microprocessors, right? Microchips, silicon chips. So have you heard that, the size at which we are right now for the silicon chip, plus minus 1 or 2 nanometers, and that will be the limit of how small we can make our microprocessors or these chips. And the reason for that is quantum tunneling, because once you cross a certain threshold, then quantum mechanics principles comes into play. And what tunneling basically is that, say, there's an electron here, these are electron here, and there's this boundary between them. Then electron can just jump over this boundary and reach here. It's as simple as that, quantum tunneling. So we use the concept of quantum tunneling here. Now, how exactly? I mean, I don't come from a physics background, so I won't get into depth of it. But so we use the concept of quantum tunneling to skip this whole crest, and we just go from here to here, and we reach our global minimum. So why I brought this up is that, as ma'am asked the question that, why don't we have some, we do have some quantum optimization algorithm. And to answer that, yes, we do. Like, this is the very first, I can actually say with confidence, and quantum annealing was the first actual application of quantum computing. Like, this was the D-Wave. There's a company, D-Wave, which was the first quantum computing company. So they started this whole era of quantum computing, and here you can, it is very simple, it's very easy to understand, easy to see that how we are getting you can say exponential boost in our performance. So yeah, there exists, you can say algorithms like this, but there are limitations to so these kinds of algorithms. Like the very first being that we are limited by the number of qubits. We are limited by the number of qubits, and we are limited by how well they perform. Okay, there is another error propagation. I'll quickly talk about it. Error propagation. So I talked about noise, right? So there is this concept that every time you pass a qubit through a gate, any gate, G gate, it adds some error to it. It will add some error to it, which will keep on propagating. And this error is very large in case of classically. It is in classical also. I think we talk about some fault tolerance and all that kind of stuff, even in classical computing. But in quantum, it is very large, like to an extent where we have to consider it in our calculations. So to answer your question, ma'am, basically the existence of that, the number of qubits are pretty low compared to your that pure quantum computers, is one of the reasons why we don't actually perform large scale optimization on a quantum computer. And the second is error propagation. But to answer your question about entanglement, so entanglement is hard to obtain in laboratory conditions. So when I say quantum inspired, I think I think you are getting confused between high grade algorithms and quantum inspired. So okay, let me just take a step back. In quantum computing, we have three kinds of algorithm. One, pure quantum, the algorithm like I think there's a you have a session on HHL and VQE algorithms. So these are pure quantum algorithms. But everything that happens in this algorithm happens on a quantum computer. We start with some state, we do some mathematics, and we encode it into a quantum computer, and we get the output. These are pure quantum problems. They're pure quantum algorithms. Then come the high-grade quantum algorithms. Isme what we do is like there's a variant of VQE which is high-grade in nature. So say this is like a feedback mechanism. We do most of the work on a classical computer, but the hard part hota hai, like if you are this I think this is interesting for those who would like to know it. You must have heard about this, AX is equal to B. Very simple problem. बचपन से करते आ रहे हैं कि हमको x determine करना है, right? This is like solution vector, I'll call it. We have to determine this. This problem is such a computationally expensive problem on an industrial standard, and there's $1 million problem. If you can find a very efficient way to do this, then you have solved many industrial problems. So in quantum computing, we try to specifically my company also used to try to solve this particular problem. And when we do that, then we can talk about a high-grade approach. In high-grade approach, we can say, classically, the classical computer just takes care of the decomposition part, like decompose this circuit, this matrix A, and so on. And the quantum computer can just focus on solving it. So here I'm talking about a feedback thing, like the quantum and the classical are working together. The classical gives some input to quantum, the quantum gives some output, and depending on that input, classical again gives some output, like feedback thing. That is high grade approach. And the third and the fourth, the one I'm discussing today, is inspired approach. An inspired approach, what we're exactly doing is, हमने principles quantum computing के ही रखे, सारे principles quantum computing के रखे, but instead of having a dependency कि मुझको exactly quantum computer पे run करे, we design an algorithm in a way कि that are even capable of being ran on a classical computer. So another other way, and this may be a class आता है quantum radial algorithm. तो उसके बारे में मैं आज basically बात करूँ. Quantum radial algorithms are the algorithm basically, that are ready to be shifted on a quantum computer. Like this QCA is basically, this is my novel approach. This is something I've worked on personally. So this algorithm, it has the capacity of being, you can say transferred to a real quantum computer if you have the resources for it. So to answer your question, ma'am, we definitely and will always, want a real quantum computer. हम जितने भी algorithm में मैं आज refer को discuss करूँगा, we will always want we have a real quantum computer to run my algorithm on. But this is an idealistic situation, ma'am, and we don't, for the problems on which industry works, we don't have that kind of quantum computer yet. For small cases, yes. If, as I said, if I want to simply optimize or find the minimum of a sin x, sin 3x function, then yes, I can do it on a a quantum computer, no doubt. And yes, I mean, to add to it, Yes, all these principles are quantum computing principle, quantum mechanics principle, and they will definitely work best on a real quantum computer. But by classically doing it, we still see some benefit. We still see key by using, by changing, let's say in this scenario, by this small change, key instead of what you do already, I think you guys already know that what we do in classical genetic algorithm is that after crossover, we determine the selected population, and from that selected population उनका जो child होते हैं, that becomes the parent. मतलब we just shift it to the next one, right? We पूरा का पूरा selected population को shift कर देते हैं next time initial population में. You get, if you know, right, उनका selected इसका initial हो जाता है, and so on. इसमें by removing that step, कि उनकी उस population का directly role नहीं होता, but उस population के chromosome से हम लोग delta कुछ निकालते हैं, उस delta से हम लोग कुछ determine करते हैं. Is a small change, a small quantum inspired change से we actually do see some benefit. मतलब me personally, मतलब I have to worked on this particular algorithm, so we have seen improved results, like, and quite a lot. As you scale up, so it improves. So to answer the question, yes, ma'am. I mean, definitely, quantum machine learning is definitely working on this whole thing. Ki, but yes, quantum machine learning is definitely working on this. Quantum neural network is a thing, by the way. Yes, ma'am. You definitely pointed. Quantum neural network is a thing.
You explained really well. Thank you, Abhiya. At least, yeah, that is there. But your constitution is also right, that we can give quantum inspired in form of ready to incorporate in quantum machine.
Exactly. Yes.
One more question. Sorry, I'm asking. But in our first session, there was a session from IBM quantum person, that was Sanjay Kumar Vishnu. So he gave idea of that we can, if we would like to run our program on quantum machine, then we can use, there was a IBM experience, there was something like IBM experience, where you are running what libraries you are using, if we or what machine.
So
which
actually,
is freely available also.
Yeah. So actually, as I said, my startup is actually a child company of IBM, right?
Okay.
So we have direct access to IBM hardware, but although because I'm also I'm more of an open source guy of myself, so I'll definitely tell you. So okay, I'll write a few things down here, just to. So IBM uses, and honestly, not being biased, but Qiskit is actually very good library. First thing, it is Python. And Python is like, everyone knows Python right now. So
but this will run on IBM experience, that same it will run, right?
No, IBM experience is like something like a GUI thing, like drag and drop thing. You drag and drop. Okay, so after, I can share my screen after some time, and I'll after we can take a 15 minutes break after 20 or 30 minutes, and then I'll show you a few of the things related to it. But okay, for now, I'll just talk about a few terms like Qiskit, and then we have Penny Lane. Here it is interesting that okay, now I assume that these things will be covered, so that is why I left it. But okay, so in this whole quantum computing thing, it is also divided into multiple architectures depending on the hardware on which we are running. One is gate based, the one which I was using, in which we had gates. One is photonics. Photonics is basically you are using photons, or the principles more or less remain the same, but if you remember from your physics background, that photons are basically packet of energy, right? So these packet of energies, the light is basically a continuous flow of these packet of energies, right? Very simple physics I'm talking about here. So photonics you can use when you are trying to tackle continuous valued problems. I mean, I haven't personally dealt with these type of problems like this. These are like more on the machine learning side. In machine learning, you can use continuous data streams to better, you can say, optimize your model and all that stuff. So then you use photonics. For quantum machine learning, photonics are very, you can say, popular. And then you have annealing, which I already told you. Annealing. Then there is this aspect of diamond head. These are like hardware. I mean, we should not be concerned about it. Diamond head technologies. So my point being, like gate based way, we have Qiskit. Photonics mein we have Penny Lane. Annealing mein we have D-Wave. And Diamond Head mein we have Atom atom computing. There's some company called like that. So depending on what kind of application you are working on, you can change. And it may be it's very good. If you are specifically working on optimization problem, then there is a language Q# from Microsoft. They have a whole language for quantum inspired optimization. Although those are limited to your simple problem like traveling TSP, traveling salesman problem, knapsack problem. But if when you are trying to get a gist of this whole thing, then QSHAP, I'll share. So what I'll do is actually, if you guys are interested, that I'll probably share a few of my articles and a few of the links along with this whole notes, which you can share with all the attendees. And if they want to explore more in this domain, then I'll be, happy to share more resources, because it is interesting. This is very interesting. Quantum automation is a very interesting field and very hot right now. Okay, so although we in this discussion we pretty much covered more important things, but to give a gist, just right now, I'll talk on a very brief level on some classical, you can say, optimization algorithm. Although I already know that most of you guys are already familiar with it, but why I'm doing this is to get a gist that why even go quantum, why do we even bother going quantum. And so in classical optimizations, first thing are just derivative based, right? We have derivative based algorithms. Derivative based. Isme, we have simple gradient descent, we have stochastic gradient descent, and these two we already know. In gradient descent advantage, we already know that so that both of them we already know they are you can say computationally expensive, disadvantage, but they are very simple to implement. These are simple to understand and implement. So we already know gradient descent we already know. Like if I were to explain both of them, it would be pretty simple. Like say, if I have this landscape, we start on some random point, we find the slope is going in this direction, so we go in the opposite direction, and luckily we can find a global minima, but we might even find a local minima. So these kind of algorithms are not well suited for what you call a scattered landscape, like this kind of landscape. It is well suited for, you can say, as more of the smooth kind, like this one. So you already know this for gradient and stochastic gradient is, you can say, and modulation or advancement in gradient descent, which talks about randomness and which is computationally less expensive than gradient descent. So that is everything, or that is all we know. That is something we already know. Then we have our bracketing algorithms. Bracketing algorithm is important because this is where the quantum advantage comes into play. So bracketing algorithm, I'll talk a bit more in detail, because bracketing I don't think is usually covered in your syllabus. Bracket is a very simple concept. We already talked about this whole solution space thing, right? So this solution space, I can also map it to a domain, right? A domain. And say, for example, my domain just lies between 0 and 1. And this is like an integer 0 and 1, not bit string 0 and 1. Then bracketing would mean that, so this is a number line, right? This is a number line 0 and this is a 1. I'm slowly reducing my domain. Like I reduce my domain. This becomes 0.8 and this becomes, say, 0. I should be 0.2 and this should be 0.8. Like I'm slowly reducing this bracket until I find the most suitable domain for my problem. Bracketing works like that. Why I'm mentioning this bracketing is, and why I mentioned this, first of all, let me tell you why I mentioned this specifically, this gradient and stochastic gradient is, see, quantum computing may we talked about this principle of superposition, right? So I gave you a good example ki if I have a lamp, right, and that's just spreading light in all possible directions. So if I'm using a quantum computer, then I won't be limited to this particular direction. There will be a possible, I will be taking the possibility ki what if I go there, and definitely this one, as we move ahead, will give me the global minima. So principles like superposition actually help me to explore the search space more vividly compared to your classical you can say gradient based algorithms or stochastic. Gradient based algorithms are anyway not that talked about in this whole optimization community because of this limitation. But here that is what I have in mind. What the context is for while I'm explaining this whole gradient descent thing. And bracketing, why I'm talking about this is bracketing, you see, so bracketing in some sense is like, I'm just trying to slowly cut off some area from my search space, right? So even in quantum computer, in genetic algorithm, that is exactly what we were doing, right? In some sense, slowly and slowly, we were trying to, like, sabse pehle to it was completely random, my population, right? Then my population could be anywhere. It could be in it, but it could be out, right? But slowly, I saw that, okay, ये अच्छा नहीं है, this is not good, this is not good, this is good, और यहाँ पे अगर एक और होता this is good, तो I give more preference to this. तो अब next time जब मेरा population बनेगा तो the possible values will be more limited. So this is in some sense is bracketing. तो जो मैंने genetic algorithm what I was talking about, that in some sense is like bracketing, not exactly bracketing, but principles in conceptually speaking it follows the same principle. That is what we are, you can say, going towards with it. अब इसी के आगे, there are other algorithms like, classical algorithm, we already have the concept of, add a grad, and Newton-Raphson method if the function is differentiable. But these things you already know, and the advantage of these Newton-Raphson is a pretty well-known method, and it's pretty famous and well used in all classical optimization aspect because of its, not I would say, simplicity and ease of you can say implementation, and it sort of I think, if I'm not, correct me if I'm wrong, it sort of always it's certain that you will converge to a solution with Newton-Raphson. If I'm not wrong, I think it is true. I'm not completely sure about it.
Again, why Newton-Raphson is not coming under bracket? It's again giving some sort of shorting. It's again giving range. Now solution lies in between.
Yeah. That is why I did not make a new section. Yeah. It's
okay.
Yeah. Add a grad and yeah. That is why. Yes. And let me see if I need to cover any more classical. Yeah, I mean another. So I think now coming to why we are even. Or maybe we talked about, okay, so I think I can skip the part when I talk about, why we are talking about this whole quantum inspired optimization, because I think I've already talked a bit about it. So, okay, now I'll talk about how do you actually approach a problem using quantum, this whole aspect. How to approach a problem.
We can one more question.
Yeah, sure.
Because that whatever concept you explained earlier, when you started with genetic, when we were talking about alpha and beta, I think PSO kind of algorithm will work better.
Yeah.
Because alpha beta, because it's like acceleration coefficient, alpha and beta also we can call like acceleration coefficient, which are taking solution towards best.
Yeah.
Well, I think better than genetic, more suitable is this kind of PSO SWAM one instead of genetic evolutionary. I think.
Yeah, the reason why I'm laughing is that yes, that's exactly what I was about to say. After
Okay.
yeah, because so actually my plan was that after this I was going to come to genetic algorithm, and then I was going to come on quantum inspired particle swarm optimization. And you are absolutely right. Like, see, particle swarm optimization itself talks about velocity and position, right? There are two aspects of every particle, and we take the velocity aspect and we just do what we did in genetic algorithm, and we, instead of making chromosomes, now we have possible velocity states. So yeah, that definitely gives you better solutions. So I have worked on both. I have algorithm genetic, and I have worked on QPSO. And yes, QPSO outperforms genetic algorithm every time. There are like multiple bases on which we evaluate the algorithm. I'll quickly go over that. But okay, now coming to how to approach a problem. Yeah. So first of all, first thing to understand in this whole aspect is that what kind of problem are you tackling? Like, what is the landscape of the problem? Landscape. This is not always possible, mind you. You cannot always know the landscape of the problem. But if you do, that is very, very, you can say, beneficial in choosing the kind of algorithm which you want to use. So landscape of the algorithm, I think I had already used these terms, but I'll do it again. One would be unstructured. Unstructured would be that this say along this, if this is a 3D one, and this whole is a, you can say, a sort of isotropic graph. Like this is the fx and x and y. This is like a two function optimization. This is x and y, and this is fxy. This is structured. This is structured in the sense that there's a continuity between them, right? This whole plane lies along the same, this whole you can say plane. Yeah, this whole plane lies along the xy axis. Yeah, xy plane. So there's a continuity in a problem. So in this, you can apply, you can every possible algorithm. You can apply your. There is a quantum, by the way, just for the knowledge, there is also quantum variant of gradient descent. But this, funny enough, that the quantum variant does not give you any benefit, because we are still using gradient descent. We are still using the slope as a, you can say, a parameter. So no, we don't get any benefit from quantum gradient descent. But it's still, there are still papers out there which talk about quantum gradient descent, but it does not give you any benefit. But okay, we can use QGAN, quantum genetic algorithm. We can use QPSO, simple ones. And now in this, even this unstructured one, it could either be smooth, it could either be rigid, you can say rugged, rigid or rugged, whatever you call it. Like, if it is something like this, and this is also smooth, but no, this is smooth. So in this, you can use annealing, quantum annealing, quantum GAN, and quantum QPSO. But now say, you have something along this line. Yeah, this would be a rugged one. And these kind of algorithms, evolutionary algorithms are better suited. I'll tell you why. So why, I am not saying that, even quantum annealing is not best suited for this algorithm. Is, we in quantum annealing, we know it's still annealing, right? It is still trying to, get in the state of minimal energy. But we have also introduced the concept of tunneling. Right, but see, in this case, see, for simplicity's sake, this should be the case. Yeah, so there are not two global minimas here, right? So when that is the case, algorithms like quantum annealing, that they fail, because what will happen is that this particle will go there, it will come again here, because see, where the whole you can say the stopping criteria for annealing algorithms is threshold. This should be the minimum it can go. But if there are two minimas, then the algorithm will completely fail. It will not know where to stop. It can need to stop here, it will just need to stop here. In these kind of scenarios, algorithms like QPSO and QGAN, why they are beneficial is, like, isi cheez ko, if I try to draw it on a isotropic, if I draw isotropic map, like, I think you understand isotropic, like this is like a particular function value. If this I'm talking about this means that मेरा graph इस तरह से होता है. This is the, you can say, the global minima, and जितना level बढ़ता जाता है, उस हिसाब से we draw concentric circles. तो इस केस में जैसे मैं अगर बोलूँ, मेरा जो ये quantum gradient descent होगा, वो ऐसे काम करेगा. मतलब वो slowly ग्राफ नीचे जाएगा. लेकिन जो जेनेटिक एल्गोरिथम होगा, वो यहाँ पे क्यों बेनिफिशियल होगा? जेनेटिक एल्गोरिथम हर पॉसिबिलिटी चेक करेगा, कहीं भी शुरू में तो इट विल बी कंप्लीटली रैंडम. इट माइट बी जस्ट केस कि वो पहली बार में ही मिनिमा तक भी पहुंच जाता है, बट दैट इज जस्ट अ रैंडम गेस. तो रैंडमनेस पे वी कैन नॉट डिपेंड, राइट? तो इसमें भी सी कि दे माइट बी द केस कि अगर मान लो इसी चीज में यहाँ पर भी ग्लोबल मिनिमा समहाउ लाई कर रहा होता, तो मेरा एनीलिंग एल्गोरिथम स्टक हो जाता सिर्फ एक ही मिनिमा या दोनों मिनिमा में कंफ्यूज रहता. बट मेरा जेनेटिक एल्गोरिथम दोनों मिनिमा अश्योरेंस है मेरे पास. आई एम प्रीटी मच एश्योर्ड कि मैं जेनेटिक एल्गोरिथम विल स्ट्राइक बोथ ऑफ दीस मिनिमास, एंड आई हैव द, यू कैन से, द फ्रीडम ऑफ ट्रस्टिंग कि वो मेरे को दोनों में से एक ही देगा, दोनों नहीं दे देगा उठा के. मतलब वो दोनों में कंफ्यूज नहीं होगा, बिकॉज जेनेटिक एल्गोरिथम डज नॉट केयर. जेनेटिक एल्गोरिथम डज नॉट केयर वेदर इट्स इन वन ऑफ द मिनिमा, इट्स इन द सेकंड मिनिमा. इट ओनली केयर्स इट हैज टू रिड्यूस द फिटनेस फंक्शन, वो कैसे भी करें. तो this is case में, the first thing which I'm talking about, depending की landscape क्या प्रॉब्लम का, you choose an algorithm. Okay, this was for continuous. Now say you have uncontinuous, like uncontinuous का, like okay, a good example would be like if I have a function, some function fx जो negative और positive दोनों values लेता है, like it is something along like this, and for sake of convenience say we ignore this values, some लोग negative values को we ignore this value, we don't consider these values, तब तो हमारे we have a gap, right? ये uncontinuous landscape बन गया. इस केस में annealing you cannot use, definitely we cannot use, because annealing तो totally works on this whole thing कि वो अपने neighbors को check करेगा. तो अगर even if it reaches here, it has no way of going here. तो annealing तो we cannot use, definitely not use. In CS में evolutionary algorithms like QGAN, and QPSO, those are beneficial. The first thing,
what in case of multi-objective?
Multi-objective, that is what I talked about right here, in which, if we have say multiple minimas.
Okay.
Yeah, then QPSO and quantum annealing are a good choice.
Annealing also can be applied.
Yeah, annealing can also be applied. Annealing, but yeah, you'll have to make sure that it stops after specific iteration, because annealing will not know like if this is what you want or this is what you want. Although in all honesty, we don't care, right? Because we, as you said, multi-objective function can have multiple global minimas.
Yeah, right? that is the problem of multi-objective, that we cannot show that will get best in both.
Yeah. So yeah, that is what the QJAN and QPSO assures that. So basically, I do have on my system. I have this thing. So we did this thing. We talked about it in one of the conferences, that one of the benefit of QJAN is that you can be assured that your quantum genetic algorithm will definitely strike, or at one point in time reach every possible global minimas. So it was I think it was, I'm forgetting the name of the function. It had 4 global minimas. It was something like these were the 4 global minimas. So we were able to show that quantum genetic algorithm will definitely and will always reach every possible global minima at least once. Because at the end it can be because we are only concerned about the minimum value, so it can give you any output. It can tell you koi bhi inme se charon mein se, but we can assure ki wo charon pe jayega zarur ek baar. So that is how you decide an algorithm when you're talking about quantum inspired thing. Uske baad second thing, how do you write a cost function? So I think I will talk about, this is a good time to basically talk about the whole QBO thing. I think QBO is point, yes, it would be beneficial. So we already see cost function. We already know about cost function in one aspect. It's like, you can say, negative of loss function. Negative of loss function. There's why in this. From machine learning, I'm introducing machine learning within it. But the point being that we evaluate our every possible, you can say, qubit on this cost function. And depending on what we are trying to do, if we are trying to increase this cost function, we are trying to decrease this cost function, we usi hisab se, we how we consider this, how we actually consider this cost function, or more better interpretation would be fitness function, actually. Fitness function. So for now, usually what we I think in general sense, we usually try to minimize a problem. We almost never try to maximize a function. So us case mein, we want to reduce this cost function, and we might want to improve this fitness function, depending ki fitness function kaise describe define kiya humne. Usually, like there's this one implementation which I did, what I did was I took a very large value, 1000, and usme se I used to subtract this cost function. I'll tell you why I did that. It's very interesting why I did that. So I used to do this, and that I took as fitness function. So इस केस में ये वैल्यू जितनी छोटी होती जाएगी उतना मेरा कॉस्ट फंक्शन ज्यादा होगा, राइट? तो होता क्या था, समटाइम यू विल वर्क विद फंक्शंस जो कि नेगेटिव में दे गो इनटू नेगेटिव डोमेन, द यू कैन से द, बट वी डोंट वांट टू कंसीडर नेगेटिव नंबर्स. उस केस में हाउ डू वी इवैल्यूएट दिस? तो उस केस में इट कम्स हैंडी. गिव मी अ मिनट. या, तो इट कम्स इन हैंडी. So, so this was
Abhigyan, so for such kind of problems we must know, no, कि हमें कितना maximum number लेना चाहिए, that should have some like, so that we are able to eliminate the negative one.
Yes ma'am, we can define the domain, like agar simple, if I have a function fxy, so I can define the domain for this x and y's, right? F, so we don't know. F, so we are trying to evaluate, so we can't, there's no way of saying if we should or we should not go in this direction. Right. Yeah. So okay, now say classically speaking, there are multiple optimization problems. Yeah, this is important that I talk about this.
Have you you have been working and you have developed this quantum optimization algorithm itself? So have you tried executing them on the CEC benchmark problems also, or some real problems you have been working on?
Yes, we have worked on NCA, well, when benchmarking problems, yes, we have worked on that. But those were now when we were trying to sort of test the, you can say, the scalability of algorithm. Now it has been moved to industrial applications. Like I'll talk about one application in the end. It's an interesting application. I think that everyone will love it. But before that, yeah, we have done benchmarking. I mean, yeah, that is how we start. We start with simple function fxy function optimization, and then we move ahead. So yeah. So say, for example, say, there are multiple type of optimization problems, right? One would be simple function optimization, which I have been talking about so far, like this fxy. I'm just trying to find the minimal of this value. Others are, say, this if w is equal to wi x naught plus w2 x1 plus w3 x2, and I want to find the most optimal weight of this whole thing, right? I mean, this is in some sense an fxy problem, but you can call it something sort of like a constraint optimization problem. Why I'm saying constraint optimization problem is that I am putting a constraint on this value of wi's. Say, I say these can be within this range. So that is the constraint, and optimization is definitely, say, we want to maximize this w. No, w and this x1 x0 x1 x2 are fixed. Then, excuse me, these are exactly the problem. I think I mentioned the term QO, right? Now QO is an extension of these kind of problems, in which what we are doing is, now wi lies within the range is either 0 or 1. If you think about it, this is nothing but a knapsack problem. Now in knapsack problem, we either pick not talking about a fractional knapsack problem. I mean, this could be extended to a fractional knapsack problem, but for now, say it is a simple knapsack problem, 0-1 knapsack problem. So we either pick an item or we don't pick an item, right? So this kind of problem, exactly 0-1 kind of thing, this you can solve using QO approach. QO, as I already told you, the full form is quantum. You can say quantum unconstrained unconstrained binary optimization. So what we do here now is that, okay, now we don't have a fitness function right now, mind you. We don't have a fitness function. We just know that this is the objective, and this is the function on which we determine our objective. How do we get the fitness function from it? For now, I'm to talk about the the QO aspect. So there's in quantum computing, there's an aspect of Hamiltonian. What Hamiltonian, and mind you, I mean, let me tell you, is only you can say important when we are talking about this QO, or in general annealing, I would say, and when we are talking about annealing. Why is it important? So Hamiltonian, what it means is, Hamiltonian, I'll draw pretty good Hamiltonian, is equivalent of energy of a body. Energy of body. So annealing में we know that a body tends to loses energy and be a state of lowest energy, right? So quantum annealing maybe the concept is same, but annealing की जगह we are talking about a term Hamiltonian. Hamiltonian, बस quantum mechanics में you can समझ लो कि it's like Hamiltonian of a body is the total energy of that body. Total energy को determine करने का summation होता है, वो summation हम उसी की बात करेंगे. तो फिटनेस फंक्शन अब annealing के केस में क्या हो गया? अगर मैं H से हैमिल्टोनियन डिस्क्राइब करता हूँ तो इसका फिटनेस फंक्शन बनता है a/2. इसका हो जाता है, हाँ, summation of psi x, I'll tell you what psi x is plus b/2 summation of hi. ये if you don't get it, it's okay, क्योंकि ये थोड़ा quantum mechanics चले. But why I'm talking about here is that at least you should know for one kind of problem कि how we convert like this. I'll tell you, like, this is very difficult because let me just complete and I'll tell you. I think that will make much more sense after I'm done with this. Ji size y size, yeah. So, okay, now let me explain each and every aspect of this equation. It might look a bit complex, but trust me, it's very simple once you get it. A and B are the coefficients. वो constant है, those. अब you उनको just हटा दो. what this ix is, अब देखो mean what mean now if you already know about a qubit, like this is what a qubit looks like ये along अगर ये z axis है, this is x axis and this is y axis. So when we talk about a qubit, हम उसके 3 axes के along we talk about it, right? तो इसके according में there is this poly like scientist, I'm forgetting the first name, but he gave us 3 parameters to determine the state of a qubit: phi x, sigma x, sorry, sigma y and sigma z. सिग्मा एक्स डिटरमाइन करता है उसका एक्स एक्सिस के अलोंग एनर्जी, सिग्मा वाई डिटरमाइन करता है उसका वाई एक्सिस के अलोंग एनर्जी, एंड सिग्मा जेड करता है जेड एक्सिस के अलोंग. वेरी एज सिंपल एज दैट. तो अब यहाँ पे नाउ इट वुड स्टार्ट मेकिंग सेंस टू यू. इनिशियली इफ यू रिमेंबर, मतलब जब मैंने ये थोड़ा सब्टल था, बट इफ यू गाइस हैव नोटेड, मैं हमेशा एक्स एक्सिस के अलोंग रोटेशन कर रहा था, वाई के भी नहीं, जेड के नहीं. जेड तो चलो करूंगा ही नहीं, क्योंकि मैं मतलब व्हेन आई एम स्टार्टिंग तो मेरे जेड एक्सिस से तो एंगल हमेशा 0 डिग्री बनेगा, तो मैं अगर ऐसे घुमाता भी रहूंगा अपने क्यूबिट को तो कुछ से कुछ होगा नहीं. तो जेड एक्सिस को हटा दो. मैं वाई एक्सिस के अलोंग कभी रोटेशन नहीं करता, तो मैं एक्स एक्सिस के अलोंग रोटेशन कर रहा था. क्यों कर रहा था? क्योंकि एक्स एक्सिस जो होता है ना, उससे हम उस पूरे क्यूबिट का ना, ये मतलब इतना जो पार्ट होता है, ये इनिशियल हैमिल्टोनियन, मतलब स्टार्टिंग में कितना एनर्जी थी उस बॉडी के अंदर, वो डिटरमाइन होते हैं. ये सॉर्ट ऑफ यू कैन से उसमें आता है, क्वांटम मैकेनिक्स के रूल्स में आता है कि व्हाई वी टेक अलोंग द एक्स एक्सिस. ये मतलब यू सेट सर्टेन थिंग्स की ये सेट कर लो, इसको रेफरेंस लेके वी विल डू अदर थिंग्स. तो उसका यह वाला समेशन के बस सिंपल ये कॉन्सेप्ट है कि स्टार्टिंग में, और यहाँ पे समेशन क्यों है, क्योंकि हम अज्यूम करते हैं कि हमारे एक क्यूबिट पे कभी काम नहीं करते हम लोग, हम हमेशा n नंबर ऑफ क्यूबिट्स पे काम कर रहे हैं. तो सारे क्यूबिट्स के एक्स एक्सिस के अलोंग एनर्जी का समेशन, बी सेकंड दूसरा कोफिशिएंट, और उसके बाद इसमें अब आता है एच आई होता है चेंज कितना, मतलब हर क्या कहते हैं टाइम स्टैम्प. मतलब मैंने बताया था हम लोग क्वांटम मैकेनिक्स वी डोंट टॉक अबाउट एपिसोड्स, मतलब अगर मतलब जस्ट टू सिंपलीफाई, अगर मतलब इफ इट वाज कंफ्यूजिंग टू से दैट कि एपिसोड ये हो जाएगा कि मेरे को पता है कि मेरा फर्स्ट पीरियड के बाद सेकंड पीरियड आता है, वो एपिसोडिक होते हैं, वो एपिसोडिक इवेंट्स होते हैं, वो डिस्क्रीट इवेंट्स होते हैं कि एक फर्स्ट के बाद सेकंड आएगा ही, सेकंड के बाद थर्ड आएगा ही. टाइम क्या कहते हैं एवोल्यूशन में क्या होता है, हम टाइम के अलोंग निकालते हैं, इस टाइम यूनिट नॉट सेकंड, इस यूनिट टाइम के बाद ये होता है, इस यूनिट टाइम के बाद ये होता है, सो ऑन. तो एच आई बताता है कि हर यूनिट टाइम के बाद कितना चेंज आता है जेड के, अब जेड एनर्जी में. तो एक हमने जेड एनर्जी कर लिया. जे आई उसका वो एक्स और जेड को कंपोनेंट को साथ में लेते हैं. ये मतलब फॉर नाउ, मतलब अभी सिंपलिसिटी से के लिए जस्ट बेयर विथ मी, एंड अभी बस समझ लो कि इन दोनों का समेशन हम लोग लेते हैं फाइनल हैमिल्टोनियन के लिए. मतलब ये वाला डिटरमाइन करता है उस बॉडी का फाइनल हैमिल्टोनियन. तो हम लोगों ने अभी क्या बात किया, हमने बोला कि हमको एनर्जी ऑफ अ सिस्टम घटाना है. तो हमारा ऑब्जेक्टिव क्या बन गया कि हमको इस हैमिल्टोनियन को घटाना है. अब उस कैसे घटाएंगे, इस एक्स को चेंज करके, इसको चेंज करके और इसको चेंज करके. और ये कैसे चेंज होते हैं, एंगल्स चेंज करके, मतलब ये थीटा एंगल चेंज करके चेंज करते हैं, ठीक है. तो वो हैमिल्टन घटाना है. अब मैं ये था कॉन्टेक्स्ट, ये कॉन्टेक्स्ट था कि क्वांटम में, क्वांटम मतलब हाँ जस्ट मतलब मैंने क्यों बोला, क्वांटम कंप्यूटर को बस यही भाषा समझ आती है. क्वांटम एनीलिंग में स्पेसिफिकली क्वांटम कंप्यूटर कैन ओनली अंडरस्टैंड दिस काइंड ऑफ इक्वेशन, इट हैज नो वे ऑफ अंडरस्टैंडिंग दिस. वो समझ ही नहीं सकता कि ये प्रॉब्लम कैसे समझाएगी. तो यू एज अ प्रोग्रामर, दैट इज व्हाट वी गाइस डू एज अ क्वांटम एल्गोरिथम डिजाइनर्स, या यू कैन से नॉट एग्जैक्टली डिजाइन, मतलब क्वांटम रिसर्चर्स आई विल पुट इन जनरल, दैट इज व्हाट वी डू. वी कन्वर्ट दिस प्रॉब्लम इनटू दिस फॉर्म. अब वो कैसे होता है उसके लिए देयर आर लाइक million, you can say thousands of papers सिर्फ इसी चीज पे. there is no one way, there is no one specific method कि do this steps or you'll get a solution. ऐसा नहीं होता. like हर प्रॉब्लम के लिए अलग स्टेप्स होते हैं. like nurse scheduling प्रॉब्लम के लिए you'll find a new paper, a different paper. ये वही ट्रैवलिंग सेल्समैन के लिए you'll find a different paper and so on. every प्रॉब्लम के लिए there is a different way. तो ये मैंने स्पेसिफिकली इसलिए पिक किया क्योंकि क्वांटम एनीलिंग में यू नो बिकॉज़ एज आई सेड कि आई मीन आई डोंट एक्सपेक्ट एवरी अटेंडी राइट नाउ जो कि अटेंड कर रहा है, बिकॉज यू नो एज आई सेड कि अभी यू नो द 2 सेशंस व्हिच यू गाइस हैव अटेंडेड एंड व्हाट यू विल बी अटेंडिंग इन द फ्यूचर, तो उसमें इतना डेप्थ में नहीं गए हैं हम लोग. तो आई डोंट एक्सपेक्ट यू गाइस टू अंडरस्टैंड एवरीथिंग, इसलिए मैं भी और डेप्थ में नहीं जा रहा हूँ. बट आई एम यू नो मेंशन यू कैन से गिविंग यू टर्म्स टू एक्सप्लोर like quantum annealing. Go Google it, go try to you know read an article on it and you know read some 1 or 2 papers on it, like see वो कैसे ये मतलब कुल मिला के मैं am trying to give you a gist to give you directions that okay, this and this, these are good directions to go into and explore into, so try to go along those lines. So just say so right now I was talking about how do we make the fitness function. So that is exactly what doing.
Abhigyan,
Yes, ma'am.
do you have some code for some optimization algorithm that you can show a demonstration for that?
Yeah, sure, ma'am. I will be switching to my system anyway. I mean, I wanted to get done with this whole writing thing, and then I'll be switching. Yeah. Then yeah. I think 5 more minutes. I think I don't think I have much more to cover. Basically, while explaining, answering the questions, most of the things were already covered.
Okay.
So yeah, so this was more or less about how we how do you approach now. I give you a problem, that is how you, so to summarize, so what I say, if I give you a simple problem, I tell you that simple, so let me give you an example. I want to optimize the shape of this pen, right?
Yeah.
So what you'll do is, first you'll ask me, how do we check if this shape is good or not, right? तो कुछ फंक्शन होगा डेफिनेटली, मतलब there's a whole structural mechanics behind it कि आप कितना टेंसाइल फोर्स है, ब्ला ब्ला ब्ला, मतलब सो ऑन. फिर मैं क्या करूंगा, अगर मैं जेनेटिकल एल्गोरिथम यूज कर रहा हूँ फॉर सेक ऑफ सिंप्लिसिटी, तो मैं सारे पॉसिबल वो कैंडिडेट्स जनरेट करूंगा एंड मैं ट्राई करूंगा, ठीक है. एंड अब उसके बाद अगर मैं पूरे फंक्शन पे ट्राई करने लग गया, तो इफ अगर किसी का स्ट्रक्चरल मैकेनिक्स में थोड़ा सा एक्सपीरियंस है, तो वो ना बहुत कंप्यूटेशनली एक्सपेंसिव होते हैं. अगर मैं सीधा इसके मतलब इस एक पेन को बनाने के लिए ना मेरे कम से कम 10-12 फंक्शंस तो सिर्फ इसका फिटनेस निकालने में लग जाएंगे, उतना टाइम नहीं है मेरे पास. तो उसके बाद मी एज अ क्वांटम एल्गोरिथम डिजाइनर, आई विल ट्राई टू simplify this function and convert it into a form जो कि quantum computer को समझ आता है. अब this could be in a different way. I talked about QO. There is the whole aspect of, you can say, QAOA quantum. Let me just write it down so that you guys can explore more if you want. Quantum approximate optimization algorithm. This is again a pure quantum algorithm. ये पूरा का पूरा quantum computer पे काम करता है. And then there's an aspect of जिसमें आजकल I am recently working is quantum surrogate modeling. Surrogate modeling, तो I think you already are aware. Surrogate modeling basically is कि we try to make a simpler model of a complex model. तो उसी का we can use quantum variant of the whole aspect. So these two things you can also use when I give you the problem. Now once you have it, now that you have a function, you see that what kind of landscape of that function is. Like, is it a smooth function? It is a continuous? Is it not continuous? Is it whatever the function is? Then you determine what kind of algorithms you want to use. Then yeah, once you have that, then you start generating results, and you cross checks, and then you have you can say you have found a use case for your algorithm, so you solved a problem. Now let me talk about because I was talking about QPSO, so I think I talked about it in a brief, but let me give you a quick glimpse of what QPSO is. So in QPSO, every particle, there is two properties associated with it. One is it is position, and one is its velocity and position. So everything is same. If you understand genetical algorithm, I honestly think I don't need to spend much time on it. Instead of the chromosomes, now the velocity of the particles, those are you can say denoted in the form of your qubits, alpha, beta, 1, right? And same principle, okay, another important thing I would like to point out, that मैंने अपने genetic algorithm, because I was talking about what I did, I use rotation gates, right? People have used other ways in to change it as well, like people have actually see, अगर मैं इसको और quantum sense में जाता हूँ, तो basically I told you that every quantum computing में जिसने कर रहे, there's time evolutions. So time evolution is like this, determined by this. This is not purely Scogren's equation, but in crude sense Scogren's equation. तो इसमें इसमें we call delta t भी add कर देते हैं, minus delta t, but अभी के लिए let's leave that. तो basically what I'm trying to tell you is, वो क्या करते हैं, there's another way doing it. हम लोग अल्फा बीटा को नहीं छेड़ते, हम लोग पूरे टाइम एवोल्यूशन को ही चेंज करते हैं. ये थोड़ा ज्यादा क्वांटम मैकेनिक्स में रहता है, इसलिए मतलब I was not planning to cover it, but now that I have introduced it, I'll just cover it quickly. तो what happens in actual sense is कि चलो अभी तक तो मैं simply I was telling you कि अल्फा एंड बीटा दो कोएफिशिएंट्स होते हैं, right? But these alphas and these betas they are itself, there's a whole equation behind this. Like alpha ko you can say cos theta, I think cos theta by 2, sorry. And beta ko you can say is e to the power minus delta t sine theta by 2. Sine theta by 2. These two things together determine alpha and beta. So so that just to I should have actually told you these. Why are we even changing delta the thetas? Because thetas का direct dependencies होता है alpha and beta पे. So by changing thetas, we are actually changing this whole alpha and beta. So some people, instead of changing this delta, they map this onto a Hamiltonian, मतलब थोड़ा quantum mechanics के sense में, and they sort of determine. I'm not remembering the exact equation, but something E delta by T by sigma, something like that, and this also delta by T by sigma y. I mean, they make it more bit for quantum mechanics, and they then use just mathematical equations to change the basically determine वो भी वही करते हैं. They also determine this delta, but how you use this delta is, there is a difference of implementation of quantum genetic algorithm in that. So just wanted you guys to know that, so that in future if if you read some paper and you see that वहाँ पे they did not use this rotation wala thing and they use some more complex mathematical equations, so you are aware कि there are multiple ways of approaching this. In some sense what we are exactly going for here is कि instead of just picking the whole selected population and putting it as initial in the next time, हम वो नहीं कर रहे हैं. हम लोग selected से कुछ property कुछ values determine कर लेते हैं, कुछ delta और कुछ theta निकालते हैं जिसको हम बाद में use करने वाले हैं. Just wanted to make it clear. हाँ, तो मतलब उसके बाद QPSO में I don't think there's much more description required कि we all, as I already said, कि concept genetical algorithm का है, बस chromosomes की जगह now we are determining velocities. अब QPSO क्यों perform better करता है, I think ma'am already said, and just to rephrase her कि QPSO में is a PSO algorithm in general, not QPSO. Is also sort of based on this physics का formulation. Like a particle can have a part, you can position and a velocity, and उसमें होता वही है कि actually say if this was a first generation तो इसमें कुछ position होगी pi and vi, and second iteration में कुछ होगा pi plus 1 और vi plus 1. तो हम इस तरीके से करते हैं मॉड्यूलेशंस कि पी आई प्लस वन पी आई से बेटर होता है, वी आई प्लस वन से बेटर होता है, मतलब इन दोनों का कॉम्बिनेशन. अब पोजीशन और वेलोसिटी का इसमें मतलब क्या होता है, मतलब हल्का सा पीएसओ में ही जा रहा हूँ एक्चुअली, अभी मैं क्यूपीएसओ की बात भी नहीं कर रहा. अगर ये मेरा लैंडस्केप है तो अगर मैं यहाँ से स्टार्ट कर रहा हूँ तो ये अभी एक पोजीशन है. वेलोसिटी क्या होगा कि ये इस पे मतलब अंदर, मतलब क्या कहते हैं, ये अंदर बोलूँ या मैं इसको अगर इसको ड्रॉ करूँ तो एक सेकंड, ये इसका सोच जाएगा. ये नीचे किस मतलब मोमेंटम, अगर पता मोमेंटम सॉर्ट ऑफ मोमेंटम वाला ही डेफिनेशन पे जा रहा हूँ मैं, जो मशीन लर्निंग का मोमेंटम होता है, जो मोमेंटम होता है उसी में जा रहा हूँ कि लर्निंग रेट क्या है, सॉर्ट ऑफ लाइक दैट. तो इसकी दूसरी प्रॉपर्टी होती है वेलोसिटी. तो हम इस तरीके से आगे मूव अलोंग करते हैं कि जो मतलब बेस्ट पॉसिबल पोजीशन पे वो जाए विद बेस्ट पॉसिबल वेलोसिटी. पोजीशन को हम लोग नहीं चेंज करते, पोजीशन तो वेलोसिटी पे डिपेंड करती है. हम वेलोसिटी को क्वांटम मतलब में हम लोग ये क्यूबिट का कॉन्सेप्ट डाल देते हैं ताकि वो जल्दी मतलब मोस्ट यू कैन से ऑप्टिमल पोजीशन पे वो लैंड करे हमारा जो पार्टिकल है. तो QPSO हो गया. आई थिंक आई वांटेड टू कवर वन लास्ट थिंग बिफोर शिफ्टिंग टू my system.
You'll be showing the application here only, explaining the application that you have done using the quantum algorithm that you were talking about.
Yeah. I'll quickly give you a glimpse here and then I'll show you the results on my system. So इनका application में what I'd like to show today is airfoil optimization, airfoil shape optimization. तो airfoil, if you guys, let me tell you what airfoils are. तो planes में you guys are aware that there are wings, right? Like if this is a plane, then these are wings, right? So this wings ka, if I put a you can say a dissectional intersection of it, so it looks like this, right? Looks like this. तो इसका shape, this height and ये किस angle पे आगे जा रहा है, all these things, these are very important. These are important in sense कि इनका shape determine करता है कि कितना fuel consumption होगा तुम्हारे plane का. तो actually my company actually me personally we worked to develop to basically do this optimization using genetic algorithm. तो this is something I have worked on personally, but बहुत सारे हैं मतलब अगर तुमको functional optimization तो हमेशा ही use case रहता है. If you really want to just optimize say a given function and find the minimal value, so that is something you can absolutely do every time. And then there's the aspect of you can say topological optimization meaning कि you want to find the best possible structure of a thing, तो वो structural mechanics में use हो जाता है. And knapsack हमारे जितने भी ये हमारे आ जाते हैं, knapsack problem हो गया, traveling salesman, combinatorial optimization problem, that is what I was trying to remember. Yeah, combinatorial optimization problems में इसका use case है. Optimization. So I think we can I think we can move to my system. So give me about 5 minutes, then I think we can move to system. Anyhow, if you have any question from whatever was covered, just see, I mean, as I'm saying again, you don't have to understand every possible aspect or integrity details right now. Just use this as a reference point. Go out there, explore at your own pace, because if even if I tried in 3 years, I cannot make you a master in this whole quantum optimization thing. So I won't try. I will just tell you what is out there. There's a whole world out there in this optimization thing. I'll tell you where to look. So go out there, have a look, find something interesting. I mean, I think if possible, I'll share my LinkedIn and email address with you guys. So if any one of you want to get in touch with me, and if you have some interesting ideas, or you have some questions, or you want to work on something in general, yes, we can absolutely do that. So that should not be an issue. So yeah, now I'm open to questions while I'm switching to my system.
Any queries? Participants, any queries, please ask.
Okay, so I'll take that as a no, and let me just switch over to my
Sure.
Yeah.
So there's one query now.
Yeah. I saw that. Are you also working with quantum cryptography? Not exactly. I mean, I have, but while I was also exploring this field just like you guys, then I looked into the quantum cryptography thing. So if you have any specific question, I can try to answer it. But yeah, I mean, that is not exactly my forte or my domain these days.
Abhigyan, any idea about how we will apply this quantum into blockchain?
Yeah, so okay, so when you talk about quantum blockchain, so first thing, there are two layers to this question. Like the first layer is key, if you're trying to break quantum, like if you want to actually not break in sense like breaking something, like there are two type of hacking, right? White hat and black hat. So here I'm talking about in white hat sense, key, can your quantum algorithms break you can say you can say the cryptography on which the whole blockchain is, the whole decentralized thing. You can say the Merkle chain, the hash function on which the whole security lies. Otherwise, anyone could just add a block in your whole ledger, right? So one aspect is that post quantum cryptography, post quantum blockchain could actually be disastrous, because blockchains, okay. I'm going a bit off topic, but I think it's an interesting thing, and I think you guys will love to hear it. So you already know about Schwarz algorithm, if any one of you has ever looked into quantum computing. So it basically finds the non-prime factors of a number. And you already know that certain cryptographic algorithms like RSA and other algorithms work on this whole basic principle, that it is very computationally very expensive to find the non-prime factors of a number, or for a large number, right? So if a Shor algorithm can break that, so you already have broken certain algorithms like this RSA and etc. So we predict that as we move ahead, there will be algorithms that will be easily able to break the blockchain's hash function. So once that happens, the whole blockchain is gone. You don't have that security and decentralized nature anymore. So that is one thing. So उस सेंस में there is a field called post quantum blockchain. तो उसमें we talk about कि okay, now how do we use this quantum computing itself to make a hash function जो कि अब कंप्यूटेशनली और स्ट्रांग हो कि उसे क्वांटम कंप्यूटर भी ब्रेक करने में एक लेजिटिमेट अमाउंट ऑफ टाइम ले. तो दैट इज वन एस्पेक्ट. सेकंड एस्पेक्ट इज कि क्वांटम सेफ ब्लॉकचेन बनाओ, कि क्वांटम कंप्यूटर यूज मत करो, बट हैश फंक्शंस का कॉम्प्लेक्सिटी, ये थोड़ा क्लासिकल सेंस में चला जाता है कि उतना कॉम्प्लेक्सिटी बढ़ा दो कि क्वांटम ही ना कर पाए. मतलब कोर प्रिंसिपल्स चेंज कर दो हैश फंक्शन के, कि वो क्वांटम उस फील्ड में, मतलब जैसे दिस अगर मतलब आई मीन ऑल्दो आई एम टॉकिंग इन फेवर ऑफ क्वांटम कंप्यूटिंग हियर, बट there are various limitation of what kind of problems you can solve on a quantum computer. Interestingly enough, you cannot add two numbers on a quantum computer. Very simple operation. We are used to adding two numbers. 1 + 1 is equal to 2. Very simple. But on a quantum computer, you cannot do that directly. My point here being that quantum computer is also limited in the sense, in the type of problem which you can solve. So quantum safe वाला जो aspect होता है वो इन्हीं चीज को determine करता है. It talks about how can we use the limitation of quantum computers, and these limitations are not in sense of hardware. These are theoretical limitations. Like you can never expect certain problems to be solved on a quantum computer. So why not use those kind of problems to make a hash function? So blockchain थोड़ा defensive भी है, मतलब है, I mean it plays in a defensive way. How do we protect our current whole architecture from this advancement in quantum computing? And yeah, looking for collaborations. I mean, yeah, I mean, I'll give you my LinkedIn. So I know quite a few people, and I have a connections in this whole company which works on quantum cryptography. So I can hook you up with someone, who will be more beneficial for a direct collaboration in quantum cryptography. As I said, it is not like my forte right now. I'm more into optimization these days and surrogate modeling. But yeah, I can definitely help you out to connect you with someone who can, help you out with this. So let me just share my screen. I mean, yeah, sure. If anyone has any other questions, you can go ahead and. So.
Any questions? I think no more questions.
Yeah. So I'll give you a demonstration, but before that, I wanted to wait. Just give me a minute, actually. So yeah, I wanted to basically show you this one, this particular graph. Not zoomed in. I think if it is visible, is it visible enough?
Yeah, it's visible. That's fine.
Yeah. So here I'm taking, say, for the sake of convenience, for now, consider that I have some fitness function. Although if I remember quite remember, it was a rastringent function.
It's written over there. It's rastringent function.
Yeah, sorry. So rastringent function in which in this I have compared your classical QGA, your classical PCO, and QPSO, quantum particles optimization, and quantum genetical algorithm, QGA. So you see that, although ma'am correctly predicted that QPSO will perform great, and what I have done is I have limited the number of iterations. The 1000 iterations is the limitation, and all the properties, all the parameters being that, the population size, the chromosome length, and all those things, those are limited. I have restricted. So you see that QPSO outperforms everyone, all other candidates by quite a margin. And you see the QGA is still. Yeah, please go ahead.
I just wanted to point out one thing. Like here, you are using the term number of iterations. So because in one iteration of GA, there may be the count of the number of times the fitness function is evaluated. That may be different from the number of times it is being evaluated in QPSO or any other algorithm.
No, that is what I said. I kept everything constant. Like
so it is the maximum fitness function evaluations you're talking about, or it is the number of iterations itself?
Here I'm talking about minimum number of iterations, like convergence rate is what I'm referring to here. Like when I limited the number of iterations, then QPSO you can see is converging to the solution at a much faster rate. So here, just for the context, as you pointed out, in QGA we have basically two important parameters, right? A number of chromosomes and number of genes in a chromosome, and number of chromosomes, the population size.
Right.
In PSO, if you know, then PSO we also have similar things. We have the number of particles, right? And how much you can say size of each particle, what is the range of values, right?
Right.
So that I have kept same.
Yeah,
So
that is still like depending upon the evolutionary, because the evolutionary operators they change between GA and PSO. The number of times fitness function, because that is going to also contribute towards the complexity. How many times your fitness function is being called. So if you check it out, that for the same number of iterations, you may have different count of the number of times your fitness function is being executed. That may also vary.
Yeah. So that is why, so what you were saying, that would be, function value versus time. That, time, how much time it takes to converge.
Yeah,
So,
that can also be counted as the time factor also.
Yeah, so even if I did that, then I can assure you QPSO will outperform, because
that is fine.
No, I know. I mean, yeah, I'm just extending. So you already pointed out. So that is why, that is just to keep things fair. So I'm putting number of iterations. I'm not considering it. It actually might be the case that the genetic algorithm can take much more time than QPSO. It is usually the case, but is that, so for the sake of showing that even if that's not the case, and even if we are considering only number of iterations, not considering how much time each iteration takes, QPSO still,
Okay.
So
do you have that diagram in which time difference, like how fast this QPSO is doing? Do you have that graph also with you right now?
Yeah, graph. I don't think. I mean,
actually, because I think, just for my curiosity, I would like to see, because I think quantum is for parallel and fast simulation, because it's like it's running that on a simultaneous manner. So I think it will give result less than, I think, I cannot say even half, more than very less time it will take as compared to basic GA and all those. But I think you are running all on quantum computer.
Yeah.
All on quantum computer.
Yeah.
So you are running all on quantum machine. So time.
So no. The thing is that
it's on the classical only. It's not on the quantum machine, is it?
No. This is on a quantum computer, because it is small problems.
Okay.
So no. The thing is that, why I have not brought it in a graph is that, when you're talking about quantum computer, so we cannot just, the time it takes is not just like I cannot say that this is the time my problem spends on a quantum computer. Why is that the case? Because I'm using a cloud service.
Right.
To put it more funny, I don't have a quantum computer at my home now. Right. So once I put a problem on IBM, say for now, let me tell you, on an IBM system, then it goes into a queue, right?
Yeah.
Then us queue mein wo kab when it will get a chance, and because I'm running it for 100 iteration, तो उसको 100 times queue में wait करना पड़ेगा. So it won't be fair to any comparison, right?
Right.
So wo issue is, that is why we don't plot time.
So that IBM machine you use by that same, as I said earlier, IBM experience, by that same you use that.
Yeah.
Like
so
how you use computer, how you use this, how you executed this on quantum machine.
Let me just show you a quick line segment.
Like actually, just initial idea. If I would like to run a code on quantum machine, how I can start with.
No, I totally get your point, and just give me a second. Actually, I'll just show you one this line, and that can actually help you. Yeah. So here, I'm actually, I'm setting get backend. So I'm sort of setting a backend here. Like backend is where my my quantum operations will happen. So I have a choice here. Say I'm using a simulator, AER simulator. So by using a simulator, basically what I'm doing is I don't have to wait in the queue, right?
The same he showed in his program first day, AER simulator. Right.
Yeah, Sanjay gave a demo for this.
Yeah, AER simulator used. Okay.
So AER is a library actually. AER is a library and it has multiple simulators. So we don't let me quickly give me a second. Let me even if I don't remember. If I don't remember the exact code where I have it, but see, I can tell you in hand. But yeah, let's just take a good Google.
Just start, not complete code, but if I would like to run my code on quantum computer, then how I
like we have some Python file and we want to execute that, and we have some code
Like
in
Collab is giving their server, same way any
Right.
organization giving their own server, their
Yeah,
own
yeah,
quantum computer to run on online mode.
yeah. Let me remember. See, because the thing is that we only move to a quantum computer when we are in production, like when everything is
Okay.
set.
set.
Yeah, if everything is set.
Right, right.
So,
But
and
no
So it's
open,
quantum
no
ready
openly
code you
available.
have.
yeah,
But
yeah,
no
yeah.
openly available.
No, they are openly available, but I'm trying to remember in which on my system right now I can have a. So let me just. Yep, this can actually help you.
Yeah.
So this is what we do.
Okay.
So you create, and I think Sanjay has already told you that you need to create an ID on this IBM Q account, IBM Quantum Experience, which you were saying, right?
Yeah,
Yeah,
yeah.
yeah, yeah.
So you create your account there, and you need to in the config file, there's a command in which you can set your there. Okay, let me just quickly go to IBM. Hmm. Mhm. Start that.
So I think we means we can create our IBM
Yeah. So
on
basically,
this. We can create
what I was
on
trying to
this.
do there is that once you've created your ID, then
Yeah,
you
yeah,
can
yeah.
get an API sort of
Right.
key. You put that key. There's another line which you need to add. You put your key there, and then you just load your account, right?
Right.
Then what happens is, depending on what kind of account you have access to multiple kind of quantum computers. Like this IBM Q16 Melbourne. This is a 16 qubit quantum computer, right?
Right. Right.
So of me and my team has access to 256 qubits or 120 qubits. Then depending on that, you put the name of the these are real quantum
So
computers
this
now.
time for on IBM Q, we will have guideline or any blog also, or even on IBM site also, how to get that
Yeah,
API and how to use that.
yeah, that's
Right.
what I mean. I couldn't log in right now. I don't think there's some issue, but
No problem.
it's
No
pretty
problem.
simple. Just you put
Yeah.
you go to your account and you say get API. It will generate an API. You just copy and paste it here, and it will happen. I wasn't sure. I mean, I wasn't aware that if I would have, if I was aware, I would have made a small Google notebook, the Python notebook, and I would have done all these things. So yeah, okay, then after you have set the device, you just execute this circuit here is just a simple circuit. I think for this example they have made a simple circuit. Yeah, so they have made a new circuit, a 2 qubit circuit, and they have this is simply a simple circuit. This is all did Sanjay talk about this bell state, um, something along those lines?
Yeah, he has
Yeah,
discussed
yeah.
this bell state and all. Yeah.
Yeah, so this is a circuit for bell state actually.
Yeah.
So
I think he executed the same program on his machine at that
yeah,
time
so yeah,
when he was
this is
doing
the
bell
what I was
state.
talking about. You save your account, you put your API key here. So
Mhm.
yeah, then once you have that, then you just execute the circuit you pass here, and the backend, whichever device you have chosen, you pass here, and you set the number of times. Shots means number of times you want to run your circuit.
Okay.
Right.
That's it. Then your job. I'll call it a job. This is something like along the yeah, this is something like a job, like a package. which gets sent to the server, IBM server. Then IBM, after you are in a queue, then you get, whenever you get access to the quantum computer, it will run your job and it will then return the results to you.
Right.
And you can just see it, it looks like this. Job, this is your job ID, and job status is job is queued, and after run, it will say job status is successfully run, and then you can see your results. So yeah, I mean, just to point out something interesting here is that we were expecting simply 0, 0 and 1, 1, right? But as I said, that there are noise in quantum computers, real noise in quantum computers. So we also got 0, 1 and 1, 0. They are not at all what we wanted. Matlab, inka koi, they had no role to play in our whole thing, but they still exist, right? So these are some of the in this case, it is not that you can say disastrous, I would say, because still this is 45%, this is 45%, so we are still getting what we want. But imagine, yes, Mr.
You are usually working on working all these quantum program on your classical machine, right?
When we are
Usually.
developing it, yes, under development, yes.
I mean to say, like whatever work you are doing on a usual day, daily, you are running that on your classical machine, because you are developing you're running on the quantum machine, or you're running on classical machine.
Depends on the algorithm, ma'am. As I pointed out, there are 3 types of algorithm. Certain algorithms will only work on quantum computers, like VQ. Yeah, but the quantum ready one, third category is I work in one, and I work a lot. I have honestly worked in all 3, like in high grade algorithms as well. But right now I'm working on optimization algorithms. But
the optimization we can run on classical.
Yeah, optimization it is inspired. If given that it is inspired, there are, as I said,
because we're not checking performance of machine. How we are not checking performance of quantum machine. We are checking performance of our inspired algorithm, how well it's doing. We are not checking how fast it's doing on classical or quantum. Otherwise, we can go for that kind of study as well.
It is basically like we are modeling our algo on the principles of quantum.
Exactly.
And then how it will perform.
Exactly. So I was telling you about this Gaussian tray function, right, which has 4 minimas. So these crosses, what these are actually, these are the you can say the plausible solution states. So this is a very idealistic solution. I mean, honestly, even for me who developed it, that every time my QGA was searching along these 4 possible states, which were the solution states. So if I remember, what I did was I increased the size of the population. So population itna bada tha ki it always found good solutions. So that I remember. But the point being ki my QGA was able to determine all 4 possible global minimas. So ये हमारा exploration में आता है, exploration के concept में आता है. We want our algorithm to be to have a good exploration rate.
We can when we are using the principles of quantum in all these algorithms, how they contribute towards the complexity?
Yeah, so in complexity, this is interesting discussion. So directly, if I talk about I think yesterday Sanjay also talked about it, but let me rephrase it. If you have a 1-bit system, it has only 2 possible states, right? 0 or 1.
Right.
In a qubit, I said, let me take an example of again. Let me put an example of a coin. When I flip the coin, although I know कि वो coin या तो heads होगा tails होगा, but until I have opened my hand, तब तक तो it is in a state in which it is between 0 and 1, right? And that, as I said previously, कि in quantum computing हम उसी state में काम करते हैं. जब तक हमने measure नहीं किया, उससे पहले हम जितने भी operation कर सकते हैं वो हम करते हैं, right? तो अगर मैं डायरेक्ट पैरेलल ड्रॉ कर रहा हूँ, क्लासिकल में अगर मैं n बिट्स लेता हूँ तो मैं 2 to the power n स्टेट्स पे ही जा सकता हूँ,
राइट.
बट क्वांटम में अगर मैं n बिट्स लेता हूँ तो मैं 2 to the power n से ज्यादा में जा रहा हूँ, क्योंकि जितने भी अल्फा और बीटा है वो तो एक रियल नंबर है, वो तो 0 और 1 में कहीं भी लाई कर सकते हैं ना, इनफिनाइट है. तो मेरी पॉसिबिलिटीज यहाँ पे बढ़ गई. तो अगर मैं डायरेक्ट कंपैरिजन करूँ तो एक प्रॉब्लम सॉल्व करने के लिए मेरे को नंबर ऑफ क्यूबिट्स हमेशा कम लगेंगे नंबर ऑफ बिट्स से.
ओके.
तो वहां पे इसका कंप्यूटेशनल बेनिफिट आ जाता है, क्योंकि मैं कम क्यूबिट्स में, कम नंबर ऑफ क्यूबिट्स में ज्यादा सर्च पेज एक्सप्लोर कर पा रहा हूँ।
Oh, okay. That way, like we are able to basically reduce the complexity.
हाँ,
In
जैसे
those terms, we can say.
exactly, this is exactly what I was talking about. This is Rosen function. ये क्लासिकल एंड क्वांटम जेनेटिक एल्गोरिथम का कंपैरिजन है. तो इफ यू सी जो क्लासिकल, जो शुरू में तो बोथ ऑफ देम स्टार्ट लाइक ऑन इन अ सिमिलर स्टेट, राइट, बट एज वी यहाँ पे जो कन्वर्जेंस रेट है क्वांटम का, दैट इज मोर, and we expect that to be the case because we already know कि quantum ज्यादा सर्च एक्सप्लोर, ज्यादा चीजें देख रहा है, तो quantum has a more tendency कि वो पहुंच जाएगा उस पॉइंट पे जहां पे उसको सोल्यूशन से ट्राई करता है. तो ये थोड़ा स्मूथ भी है क्वांटम स्मूथ, आई मीन स्मूथनेस इन दिस केस इज जस्ट बिकॉज वी हैव ऑलरेडी फाउंड द बेस्ट पॉसिबल आंसर, तो वो तो स्ट्रेट लाइन ही बनता जाएगा. तो दैट इज दैट. तो these were the 2 points which I basically wanted to sort of demonstrate and sort of prove my point. क्योंकि whenever we are talking about quantum, तो 2 ही चीज हम लोग ध्यान रखते हैं, एक कि उसका कन्वर्जेंस रेट ज्यादा होगा और दूसरा उसका एक्सप्लोरेशन कैपेसिटी और एक्सप्लोरेशन रेट ज्यादा होगा किसी भी क्वांटम इंस्पायर्ड एल्गोरिथम के लिए. तो इफ यू हैव दीज 2 things in mind, then that's it. That is how you would say prove, or say let me talk from business perspective. If say you are a company and you work on optimization problems and you want to explore if it's quantum is a thing for me or not, like should I even invest in quantum or not, then these are the 2 things which I'll tell you: key exploration space and this convergence rate. If these 2 things, which are 99% of times is what companies want, is what you want, then quantum might be the solution to you. And now let me see if I have a demonstration. I can give you a quick demonstration. And okay, yeah, this is also interesting. So this might not make much sense to you, but this was an airfoil actually. This was supposed to be airfoil, but quantum genetic, my QG algorithm, it determined if you have a tilt here, if we tilt the shape here back here, then we can improve the performance of the whole thing. So this was this gets very interesting. Once you, right now I cannot run it because my computer will crash because it's a very heavy problem. But the thing is that like the simple algorithm, the QGA itself will just act as subroutine. यहाँ पे what I'm doing is, like, मैंने QGA बना लिया. Now I have a quantum inspired algorithm. Now I'll keep that QGA as a subroutine. That itself is a subroutine now. I will work on my classical problem, and my classical problem will keep on sending input to the QGA और feedback लेता रहेगा. एक loop बना दिया. This is again a high-grade algorithm. So what I'm doing now is, मैंने एक quantum inspired algorithm को एक feedback loop में डाल के एक overall high-grade algorithm बना दिया, जो quantum और classical दोनों के साथ में mixture में काम करता है. So that is, possibilities are endless. And why these are endless? Because we don't have a quantum computer right now. जो टेक्निकली स्पीकिंग हम तो चाहेंगे कि सारा काम क्वांटम कंप्यूटर ही कर दे, बट अभी वी डोंट हैव दैट काइंड ऑफ क्वांटम कंप्यूटर्स, एंड वंस वी डू, देन डेफिनेटली.
Can you show some code for any of these QGA or QPSO that you have, like how you are creating the initial population code and your gates you have incorporated?
Yeah, QGA I can, I guess. QGA I can.
Please increase the size
of
the text.
Yeah, I'll do that. Wait, let me open a different view. Yeah, this should be.
Yeah, it's fine. Right? Yeah, it's fine. Yeah.
So I cannot get to the intimate details because this code is in a deployed right now.
Yeah, that's fine.
I'll just quickly give you overview. So steps same है, just as I explained. कि सबसे पहले I'm starting with a population, right? So let me come to this population aspect. Yeah. So यहाँ पे this is like I'm running a single generation now. So what I'm doing here is this reset is nothing but मतलब मैं सब कुछ 0 पे reset कर देता हूँ every time I'm starting a new iteration or new generation. ठीक है? तो आई एम जस्ट रीसेटिंग इट. ये सारे फंक्शंस आई हैव डिफाइंड इन अदर पाइथन फाइल. फॉर नाउ आई एम जस्ट टेलिंग यू व्हाट हैपेंस इज रीसेट सबको जीरो सेट कर देता है. एच बैरियर मैंने क्यों लिखा है, क्योंकि यू नो इफ यू रिमेंबर मैंने एच का एक पूरा लाइन ड्रॉ किया था. हर क्यूबिट के लिए एक हैडर गेट था. तो एक एच बैरियर बना दिया. और जो मेरा आर एक्स गेट था, जो मैं कह रहा था कि पैरामीट्रिक आर मतलब एक्स गेट है, उसको मैंने यू बैरियर यू गेट basically ना मतलब जितने whatever howsoever gates you study, do you can this is like a universal gate in sense कि you have three parameters: angle along x axis, angle along y axis, angle along z axis. अगर you know these three things तो तुम क्वांटम कंप्यूटिंग में कोई भी गेट बना सकते हो. तो what I'm doing here is कि मैं यू गेट के अंदर वही जो मैंने कहा था कि आई एम डिटरमाइनिंग द पैरामीटर्स की वो डेल्टा वैल्यू से कितना रोटेशन शुरू में जीरो होगा, बट एज वी मूव अहेड ये बढ़ता जाएगा. मतलब डेल्टा बढ़ेगा घटेगा डिपेंडिंग ऑन की सिलेक्शन के क्या मतलब सिलेक्टेड पॉपुलेशन में कितने वन थे कितने जीरो थे. तो वो करता हूँ. उसके बाद आई जस्ट मेजर. दिस इज द क्वांटम सब रूटीन, इसलिए आई मार्क्ड इट. दिस इज द वे द होल क्वांटम थिंग हैपेंस. उसके बाद तो आई एम जस्ट डूइंग द इवैल्यूएशन पार्ट. मतलब सबको इवैल्यूएट किया, टूर्नामेंट सिलेक्शन किया, थीटा वैल्यूज अपडेट करी, मतलब व्हाटएवर अपडेट किया, क्रॉसओवर किया, म्यूटेशन किया. तो इसमें लेट आई थिंक इफ आई रिमेंबर करेक्टली update theta values might be a bit interesting to theta values. हाँ, so if you see this update theta values is इसमें हमने जो मैं कह रहा हूँ कि जो जो हमें सिलेक्टेड क्रोमोसोम्स होते हैं उसमें हम डिटरमाइन करेंगे कि मैंने मतलब एक अलोंग एक लाइन मतलब एक कितने वन आ रहे हैं मेरे एक जीन में, कितने जीरो आ रहे हैं मेरे एक जीन में. उसके अलोंग या तो मैं एक उसकी डेल्टा बढ़ाता हूँ या घटाता हूँ. और डेल्टा डिटरमाइन करने के लिए आई थिंक एक और फंक्शन था ऊपर डेल्टा. हाँ, डेल्टा ओवर टाइम कम
इसमें just to interrupt,
हाँ
what we are saying is we are checking chromosome by chromosome, like एक क्रोमोसोम में हमारे पास कितने जीन्स वन है और कितने
नहीं
जीन्स
नहीं
जीरो
नहीं
है.
नहीं
और
एक सिलेक्टेड पॉपुलेशन में मैम
हाँ
अगर मैं इसको अगर मैं एक मैट्रिक्स ड्रॉ करता हूँ
राइट
मतलब
राइट, हाँ
हाँ,
तो
एक मैट्रिक्स
उसमें
करता हूँ तो एक
जीरोथ कॉलम
हाँ
में
एक
फर्स्ट कॉलम में हम चेक कर रहे हैं.
एक रो में कितने वन है.
इज इट कॉल रो में तो फिर वही एक क्रोमोसोम ही बन
नहीं
जाएगा
सॉरी
ना.
कॉलम सॉरी
हाँ
यस
कॉलम होगा ना फिर.
एक
हाँ
कॉलम में कितने वंस आ रहे हैं
हाँ
उसके, क्योंकि बेसिकली मैम एक कॉलम क्या डिटरमाइन करता है, एक कॉलम में क्यूबिट है.
राइट.
तो हम उस क्यूबिट में
वन कॉलम इज वन क्यूबिट और वन जीन is one qubit.
वन जीन इज वन क्यूब. नहीं, जीन तो मैम जेनेटिक टर्म के यू कैन
हाँ
से वर्ड में कहेंगे तो वो जीन है, बट
हाँ
इन एक्चुअलिटी वो जीन तो एक क्यूबिट है ना मैम.
हाँ, तो उसमें जैसे वन
हाँ
कॉलम होगा तो वो सारी
हाँ
पॉपुलेशन के
हाँ
क्यूबिट्स हो गए ना.
हाँ, वो सारे पॉपुलेशन का वो एक क्यूबिट हो, उस पोजीशन का एक क्यूबिट हो गया.
हाँ तो
तो
इसका मतलब हो गया कि हम पूरी एक तरह से पूरी पॉपुलेशन की एक्स एक्सिस पे हम देख रहे हैं.
एग्जैक्टली मैम. यस मैम.
इजंट इट, क्योंकि ये सारी डायमेंशंस हो गई ना.
यस मैम. तो उसी के अलोंग हम लोग उसके, क्योंकि हम लोग जो थीटा डिटरमाइन कर रहे हैं मैम वो उस एक क्यूबिट के लिए कर रहे हैं. वो तो हर एक क्यूबिट के लिए अलग थीटा आ रहा है.
हाँ
वो
ठीक
उस
है.
क्यूबिट के लिए आया तो ओवर टाइम वो थीटा की वैल्यू जनरेशन के साथ साथ कम होती रहेगी, क्योंकि एक्सपोनेंशियल डिके हम एक्सपेक्ट करते हैं ना. वी एक्सपेक्ट
हाँ
कि धीरे जितना हम आगे जाते जाएंगे उतना हमको चेंजेस कम करने पड़ेंगे. तो उसके से हमने एक एक्सपोनेंशियल डिके जो डेल्टा है जो हम कह रहे थे जो हम माइनस सब्ट्रैक्ट कर
हाँ
रहे हैं,
हाँ हाँ
वो
हाँ.
एक एक्सपोनेंशियल डिके फंक्शन होता है जो कि डिटरमाइन होता है वन नंबर ऑफ वंस के अकॉर्डिंग.
तो वो सिर्फ हम एक्स एक्सिस का ही करते हैं या बाकी डायमेंशंस का भी
नहीं,
करते
बस
हैं?
एक्स एक्सिस के अलोंग करेंगे क्योंकि हम लोग
ओनली एक्स एक्सिस.
हाँ ओनली एक्स, सबका एक्स एक्सिस एक्स 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 एक्स.
ओके ओके
तो बस
फाइन.
दैट्स इट. वंस यू हैव दैट तो दैट इज द होल जेस्ट. उसके बाद तो जस्ट कॉलिंग वन थिंग टू अनदर. That is the whole gist of, you can say, the QGA
ठीक है.
algorithm.
या
So I can, if you want, I can quickly, yeah, I can do one thing. Yeah, just give me a minute. I can actually demonstrate this QGA once. There's a simple example. Function minimizing the function is simple example.
या
So bump function, let me do simplicity से के लिए मैं bump function को भी खोल देता हूँ. Actually कैसे दिखते भी होता है. Now let's see. I have a lot of functions I can use. For example, say this is the function I'm trying to optimize. This is branding function. So तो this, तो दिस इज व्हाट माय लैंडस्केप लुक्स लाइक. तो यहाँ पे वैसे भी दिख रहा है लैंडस्केप इज स्मूथ एंड इज कंटिन्यूअस इन नेचर. तो we could use anything, मतलब I could have used, yeah, I could have used annealing model here, but because I'm talking about QGA, this demonstration is about QGA, so let me just use QGA for now. So this is the heat map for it. तो हीट मैप में वी कैन सी कि हमारा जो सोल्यूशन स्टेट होगा वो इस अलोंग इस कहीं लाई करेगा कहीं, मतलब. और हाँ, वी कैन ऑल्सो सी कि ब्लैक के सबसे लोएस्ट पॉसिबल वैल्यू यहाँ पे 0 पे जा रही है, तो हमारा जो आंसर होना चाहिए वो भी 0 पे ही जाना चाहिए. तो जब तक ये रन हो रहा है, लेट मी टेल यू मैंने क्या क्या पैरामीटर्स पास किए. क्रॉसओवर प्रोबेबिलिटी, क्लासिकल वाला क्रॉसओवर की कितनी प्रोबेबिलिटी है, नंबर ऑफ जनरेशंस कितने होंगे, नंबर ऑफ एक एक क्रोमोसोम का कितना, नंबर ऑफ जीन्स कितने होंगे, नंबर ऑफ पॉपुलेशन कितना होगा. आई थिंक थोड़ा ज्यादा सेट है, बट
हाँ, that's fine.
we best,
or you can reduce it, it will take less time then.
Yeah, but although just I think it's better if I reduce it.
Yeah, it's better.
Yeah.
Reduce the number of genes also.
Yeah.
I think let it be, or
let me see Rosen function. It might be because see, if you can see here, I have like 7 different versions of the same algorithm.
yeah, I can understand.
And this I have worked on so long that even I don't remember exactly which one was working.
Or let it be. Let it. I think 100 iterations won't take much time.
Yeah.
Just check.
Yeah, I mean you can see this one.
Yeah, we can see this.
Yeah.
One.
This should be, this was only 100 times, and the chromosome, the population was very slow.
Yeah,
but still you can see we got about 0.01 something.
Yeah.
So
right.
For Rosen function, you can see the minima was 0. So
it's very good.
Still, it's a 0. But if we increase the number, it will go on to increase, and so you can determine the number of the best possible chromosome, whatever the best possible chromosome was. Like this was, see, this chromosome is nothing but a bit string value, but you can convert it to integer and you get X and Y's from it.
Okay.
And and just so this was the exploration thing, how it reached the global minima. So you can see it it searched everything along this line in 100 iterations also. So that is like that is, which means that it has a good, you can say, exploration ratio. So that would be you can say a sort of demonstration. Although I would say that they are simpler algorithm. Like this was not complex, but I would say still there was a lot of thing happening in the background. They're simpler, like you can go to I'll share a few links definitely, but you can go to D-Wave's website. So they have solution to these traveling salesman problem, knapsack problem, the problems which we are familiar with, the combinatorial automation problem. These types of problems, you guys might have another look at it, and it will actually help you to build an intuition of this whole thing. Yeah, I mean, so that would be pretty much it from my side. If you guys have a question, I'm open to questions.
Any questions? Participants, any questions? Can we have a one pick?
Yeah. Everyone, please switch on your cameras. All are requested to switch on their cameras, please.
Please switch on your cameras. Okay. Okay, thank you, Abhigyan, for a wonderful session.
Thank you, ma'am. It was a
And
pleasure.
I also thank Anuja for a wonderful queries and to make a session very interactive. And once again, thanks, Abhigyan.
It was really a wonderful session, Abhigyan. Really.
Yeah,
We
Vigyan,
learned a lot.
I
Yeah.
Thank
yeah,
you,
I
ma'am.
also would like to say it's really a wonderful session and hope we'll have discussion further with you in future. So if we will face any problem, we'll again get back to you through mail or anything else.
Yes,
So
sir.
I
Yes, sir.
will, yeah. Thank you again. It's really a great session. And you explained and you resolved all our queries very well. Thank you. Thanks a lot.
Thank you, ma'am. Thank you. It was a pleasure. Thank you, ma'am.
So with this, we come to the end of this session for the day.
So next we will meet tomorrow. Okay. Okay, thanks, Abhigyan.
Thank you all. Thanks, organizer,
Thank you, ma'am. Thank you, ma'am.
Thank you.
taking a big yarn here on our this session summer school, and we learned a lot. Thank you, Vigyan. Thanks.
Thank you, ma'am. Thank you.
Yeah, thanks, organizers.